Good afternoon, everyone. We are going to continue with the next segment of this interesting, very interesting in memoriam Congress of our dear friend, Professor Osiewicz. I'm going to introduce our next speaker, keynote speaker, Dr. Guillermo Morales Luna. He received a BSc degree in mathematics from the Mexican National Polytechnic Institute in 1977, the MSc, Master of Science degree in mathematics from Mexican Research and Advanced Studies Center, CIMBESTAF, IPN, in 1978, and the PhD degree from the Mathematics Institute of the Polish Academy of Sciences in 1984. Since 1985, he is a researcher at the Computer Science Department of CIMBESTAF IPN. His research interests include cryptography, complexity theory, mathematical logic, and quantum computing. He has been visiting professor at several Mexican universities, and he spent 2 sabbatical years as researcher in the Mexican Institute of Petroleum. He's a Mexican national, and he also holds Polish citizenship. Welcome, Doctor. Go ahead with your presentation.
Thank you very much. Let me share my screen. Can you see my presentation?
Yes.
Okay, let me put it in full screen. I hope there will be no any problem. Is it okay? ¿Ya?
Sí se ve, aunque sería bueno que la pusiera en pantalla completa, ¿no?
Así está.
Okay.
Okay. Well, thank you very much for your kind presentation and for the opportunity to address to the current audience. It has been a very interesting conference, and for sure it is very significant to remember Professor Osiewicz. I met Professor Osiewicz mainly in the activities of the Polish Mexican community. Here in Mexico, we have a society, we have a formal Polish Mexican society. In fact, I chaired this society for a period. And our main social activities were the yearly Christmas time, Gwiazdka, Easter, Wielkanoc, and also a celebration in May, Majówka. And Zbyszek was a frequent attendant to these celebrations. In Mexico, we have had the privilege to have many physicians and mathematicians from Poland who established here in Mexico and spent a long time in Mexican universities and centers of research. I should mention Professor Jerzy Plbański, who was a professor in the physics department of my institute, Professor Bogdan Miernik, who unfortunately passed away last year, Janusz Haratonik also, who came from Wrocław, and who was a professor in the Mathematical Institute of UNAM, and Also, we have here Professor Olga Wiberstein, who emigrated from Poland just before the war, and he lived a long time in Canada, then in several countries in Latin America, and for almost 30 years he was a professor in Mexican National Institute, Polytechnical Institute. So I am very close to Polish mathematicians here in Mexico and in Poland as well. I got my PhD in Warsaw, and I know rather well Poland. Well, let me talk about superdense coding and a kind of communications based on quantum computing. So in the first part of my talk, I will recall the Pauli transforms and Bell bases, for which the Bell bases consists of maximally entangled states. And in the second part, I will focus on several level quantum states. Usually, a qubit has two possibilities to get determined, either to get a 0 or to get a 1. So there are just two levels, horizontal or vertical. And in the case of quantum states of several levels, we may have several levels. Let's denote by H1 the two-dimensional complex Hilbert space, and by H2 the tensor product of H1 with itself. This is a four-dimensional complex vector space, and the Bell basis of H2, which consists of maximally entangled states, is formed by these vectors.
Yeah,
here,
excuse me. I think we don't see the slides change.
Oh, sorry.
Okay, thank you.
Yes, it's okay now.
Oh, sorry. So let me begin in the first part. Okay, so I'm showing here a picture of the main building of Wrocław University, and by returning to my talk, the Bell basis consists of four vectors, maximally entangled states, which are this addition. And here we have, I would like to remark that the index are complementary in these parts. J takes one of two values, either 0 or 1, and I takes also one of two values, 0 or 1. So here we have four basic states. The basis, the Bell basis, they form the Bell basis of H2. H2, as I said, is a four-dimensional complex space. And the Pauli matrices are these four matrices. They are all, they are also as well a basis in the space of matrices. And we may number the Pauli matrices in this way. 0, 0 corresponds to the identity matrix. 0, 1 corresponds to the switching matrix. 1, 0 corresponds to sigma z, which is a change of phase phase. And sigma 1, 1 is sigma y. And we may also consider the polymatrices act on H1, on the two-dimensional complex space. And if we get the tensor product of the identity matrix with the polymatrices, we got these transformations in H2. And these transformations transform any Bell vector into another Bell vector. And if we apply any of these transformations to B00, we may get any other vector by a corresponding transformation, by a corresponding unitary action, unitary map. And in this way, whenever we fix one of these vectors, the image is univocally determined by one of these transformations. If we consider this cyclic group on the unit ball of the complex numbers, then the poly group can be represented as the Cartesian product of R4 times the collection of poly transformations, and the multiplication table of this group is given by these relations. So they have the structure of a finite group. And also we may consider the tensor product of H2 times H1, and this will be the threefold tensor product. This is a complex vector space of dimension 8. The 8 is 2 times 3, 2 to the power 3, and whenever we calculate we consider the n-fold tensor product, we will get a Hilbert space of dimension 2 to n. And in this space, in H3, we may consider also this basis, the basis considered obtained in this way. Here again, we have a complementary pair of indexes, 0 and 1, and G and K vary in this in the set of classical bits 0, 1. So we have 4 possibilities for the pair G and K, and 2 possibilities for the exponent I. We may take either the plus sign or the minus sign. So we have here 8 vectors, and they are indeed orthogonal according to the canonical inner product of this space. And also we may consider this kind of transformations. This is the identity matrix sigma 0, 0, and with tensor product with the poly transforms. And in this case, we have that whenever we apply any of these transformations to the first vector in the Bell basis, we will get the other vectors. But this time, it is not univocally determined the image. In fact, any vector in the Bell basis can be obtained in 2 ways. For instance, B000 and B00 can be obtained by applying here sigma 00 and sigma 00, or applying in these 2 cases sigma 1, 0 and sigma 1, 0. In this case, we have that any other vector in the Bell basis can be obtained in two ways by these transformations. And so whenever we apply one of these transforms to the first vector in the canonical, in the Bell basis, we are going to get a vector, a line, which is a scalar multiple of this other second vector in the canonical, in the Bell basis. And in fact, the indexes are obtained in terms of these indexes by these relations. The first is obtained in this way, and the second and the third, depending on the transformations applied on this side. Here we have the control node. We may take either epsilon 0 as an argument bit, or delta 0 as a control bit. Whenever the control bit is on, then we have the switching transform. 0 is converted into 1, and 1 is converted into 0. And whenever delta 0 is 0, we have the identity matrix. So no change is on in the argument bit. So this is a control node. This is another view of the Broad University. And this control node is a very interesting map, which has great importance in quantum computing for building computing gates. And using this transform, we may define recursively this kind of transformations. Cn1 is the control node, and Cn plus 1 will have one argument more, and it is the control node of delta 0 times this transform. The transform in the step before. Then we may get that for all n, Cn2 is a balanced map. It means that the inverse image of 0 is 2 to the n, and the inverse has cardinality 2 to the n, and the inverse image of 1 is also has cardinality also 2 to the n. So this is a balanced map. And by proceeding in this way consecutively, we may consider H4. H4 is a 2 to the 4 dimensional Hilbert space. 16 dimensional Hilbert space. And also we may consider this tensor product of transforms. The factors are Pauling matrices, and the first one is the identity matrix, is the identity map. And it can be observed that if we apply these transformations to the first vector in the Bell basis, we are going to obtain a scalar multiple of another vector in the Bell basis. And in fact, the indices are given by this transformation. but the control not obtained in this way. And the other indices are related to the first one through these relations. Okay, I forgot to mention something which is important, and the title of my talk is super dense coding. So we wondered where super dense coding appears, and it appears in this way. It appears super dense coding is getting from this table. Imagine that Alice and Bob are going to communicate, and they fix an entangled state, an entangled system. Any of these vectors in the Bell basis. Alice is acting on the second bit, and Bob is acting on the first bit. Alice is acting on the second particle, and Bob is acting on the first particle. So when they apply this transform, Bob does nothing. Bob applies the identity transforms. He makes nothing. And Alice may choose any of the polytransform and act on her qubit through this application. So if they fix first any of these vectors, Alice sends her qubit to Bob, and then Bob will get the whole system, and he measures the system in the Bell basis and will get any of these vectors with probability 1. He will get any of these vectors, and when Bob realizes which vector he obtains, he will know which was the transformations applied by Alice. But this transformation is determined by 2 bits, by 2 classical bits. So it means that Alice is sending just 1 qubit, and Bob is getting 2 classical bits. This is super dense. Alice just has to send the one half of the number of classical bits that she wants to transmit in order to complete the transformation. So this is a super dense coding, and whenever we get this kind of transformations, then Alice can repeat the protocol or make the protocol simultaneously to Bob, to some guy which is called C, and which other guy which is called D. So Alice may communicate with B, with C, and with D simultaneously, and make this kind of supercoding with 3 participants, with 3 receivers. And we may continue in this way with many other qubits. We may form the tensor product H sub n, which is H sub n-1 times H1, and we may consider this Bell basis. And here we have 2 to the n possible vectors, and they are mutually orthogonal. They form an orthonormal basis in Hn, whose dimension is 2 to the n. And we consider these transformations, and whenever we apply to the first vector in the Bell basis, we are getting other one. We are getting the line along any other vector in the Bell basis. And the relations of the indexes with respect to these indexes are given by these transformations. So these are direct generalizations. But for the case of n equal to 3, we have that any vector in the Bell basis is realized twicely as the image of polytransforms. And whenever we have n greater than 4, then for any vector in the canonical basis, we will have this number of possibilities to get this vector. So in order to communicate in an unique way, we should introduce a kind of quantum coding just to fix one vector representing the class of 2 to the n4 vectors. These are technical matters, and they are a little bit, let's say, complicated. But super dense coding can be done. Here we have that Alice that is broadcasting her messages to several receivers in uses super dense coding. And so whenever we have a collection of index, we may identify the operators that has been applied, and the relations are, and it can be done also for any other vector in the canonical basis. As I have explained before, I always use here the first vector in the canonic in the Bell basis. It is not necessary just to begin all the things with the first vector. We may have any other vector in the Bell basis, and through these transformations, we may get other vector in the canonical basis, and the relations among the indexes is well determined. Let's say is well determined. Well, in this case, we have just two quantum levels: a spin, or horizontal spin, and vertical spin, 0 and 1. But we may have a system with several quantum levels. So in this case, we are going to codify any quantum level by a power of the unit root of the unit. So let's take as rho k the primitive k root of unity. This is a point in the unit circle of the complex plane. And we take as h1 to k the k-dimensional Hilbert space, complex Hilbert space. It is the same thing that we have done before, but before k was equal to 2. Now we are considering any k. And we consider the canonical basis in this k-dimensional space. I'm showing here an an image of the Wrocław main square, and in this side there is a statue of a Polish poet, Alexander Fredro, who lived in the 19th century, a Romantic poet who was contemporary to Frédéric Chopin. And after the Second World War, Poland was moved to the west. So western part of Poland that used to be part of Germany were incorporated into Poland, and eastern parts of Poland were incorporated to Ukraine, Belarusia, and Lithuania. Yeah. And this statue of Fredro lies firstly in Lwów. Lwów is a city who at present time is in Ukraine, and the famous Scottish book, the Scottish Cafe, where the Polish mathematicians used to take a coffee and to do mathematics, lived there in Lwów. So after the war, many inhabitants of that city were moved to Wrocław. Of course, it's interesting. It's an interesting part of the history of Poland, which is not well known by Mexican students. So that's why I'm taking the freedom to mention this point. Okay. So now we are going to consider concatenations of quantum states. These concatenations are tensor products of quantum states, which are points in the unity sphere of HK. And whenever we have the tensor product of HK, we are getting n Q registers. And the Bell bases in this case are generalized in this way. When we have when n is equal to 2, then the first Bell basis is getting in this way. Here we may see that the indexes are shifted, are rotated. The index in the second vector is a rotation of the index in the first place, and the scalar product here is this power of the k primitive root of unit. And if we put these vectors as columns of a matrix, then we are going to get an orthonormal matrix. They are representing it represents an orthonormal basis of this space. Here n is equal to 2. And the similar transformations of Pauli matrices are given by these matrices. These are unitary matrices, and they are of order k times k. And each of the entries are calculated in this way. This delta is the Kronecker delta. The Kronecker delta, it means that they give the value 1 whenever the indices are equal, or 0 otherwise. So they are direct generalizations of polymatrices, and they act in the canonical basis in this way. The canonical vectors are transformed into the canonical vectors, or multiples of the canonical vectors, because they are unitary transforms. And when you consider the tensor product of the identity matrix times these matrices, then when applied to the first vector in the Bell basis, we are getting another vector in the Bell basis. And in fact, the index of this vector are the same as the index used in this transformation. And also, we may consider a kind of controlled knot defined by just by rotating the identity matrix. And when multiplied by these transforms, we are getting another transform, another matrix, a diagonal matrix obtained by these relations. And we may get this kind of identities, which are giving a collection of relators in the algebraic group formed by these transformations. So we will have a presentation of the group and the product in the group can be synthesized by this relation. So these are very easily computed, and when we apply this transformation into a Bell vector, we are getting another Bell vector. And the way in which the indexes are transformed are very well calculated. So this will allow to mimic super dense coding, but now whenever Alice acts on his Q system through these transformations, Bob will get two indexes. We'll get k squared indexes. So by one, when Alice sends just one Q system, Bob will get k squared a pair of indices between 0 and k minus 1. So this is the kind of super dense coding that can be done with several computing levels. And just as a final way to generalize all this kind of things, now let's consider hk to the k. And this space is the k-fold tensor product of H1. H1 is the k-dimensional complex space, complex Hilbert space. So the dimension of this space is k to the k. So the growth is rather quick of the dimensionalities of these spaces. And also we may consider a kind of Bell bases, which are formed in this way, where here we are rotating the canonical basis, the canonical vectors through the indexes pointed in this way. And it can be seen that the obtained basis is indeed orthonormal. It's an orthonormal basis in this space, and they are k to the k. The cardinality of this set is k to the k. And also this kind of transforms, when applied to a vector in the Bell basis, will get another vector in the Bell basis. And the collection of indexes can be calculated by these relations. So again, Alice must communicate with k participants, with k minus 1 participants, and she acts on any shared entangled system with the other through these transformations. And when the other parts receive the qubit sent by Alice, they may recover the whole information. Well, this is a kind of superdense communication. But unfortunately here, we do not have one-to-one correspondence. So many transforms will produce the same vectors. And the number of repetitions is given by this transform. So Alice and their correspondence should agree in a way to recognize the information that has been sent. So it's necessary to consider a very special quantum code just to have a one-to-one correspondence between vectors and transforms. And well, this is the number of repetitions that should be avoided in the communication process. Well, so we may consider two transforms equivalent if whenever they act over a basis, a fixed vector in the Bell basis, they are considered equally. So this introduces an equivalence relation, and when we take the quotient space, we will get canonical representations in a quantum coding. That's the point. Well, these are very technical matters. So let me continue. And it's possible to codify and decodify in a unique way the information. Well, so that's all for my talk. Thank you very much.
Thank you. Thank you, Professor Guillermo Morales Luna. I apologize. I arrived 1 minute late and I could not introduce you, but I'm now thanking you for your very, very learned lecture. And any question, please?
Valentina.
Yeah.
Yeah, this was a very interesting talk and very inspiring. Can you maybe say more about using category theory for quantum logic? Because quantum logic means to be a big problem, at least in theoretical part of quantum computing. And there's an attempt by the Oxford School to develop, to use category theory to capture this computation.
Yeah. Thank you. No, unfortunately, I'm not acquainted with the relation between quantum computing and category theory. In fact, in computer science, in formal computing science, there is a process algebra. And within the process algebra, category theory is very strongly used. I would like to pursue a line of research between quantum computing and formalizing of this paradigm with process algebra, and then go into category theory. But it is just a very first idea, and I didn't pursue it still.
Dr. Garrett has a question too.
Yes, Garrett?
He's trying to unmute.
No se escucha, profesor Garrett. Tiene apagado su micrófono.
Yes, yeah, my first comment, I lived in Wrocław for 5 years and enjoyed your pictures. I worked at the Institute of Theoretical Physics. I was cooperating with people there, including Zbyszek Ojewicz. But my question is regarding your Bell bases, and I think it's very closely related to how Timothy Howell and Chris Doran also wrote a similar paper using basically the poly matrices. I'm just wondering whether you're familiar with their work and whether it isn't very similar to it. It looked like to me.
I see. Thank you. Well, similar, yes, several authors have presented also the generalized unitary transforms that I have presented here, but they refer otherwise. I would like to emphasize the computable transformations with regard to the indexes. There are many similar studies with this kind of generalizations of polymatrices. But my point here was to point out the way in which the classical bits can be manipulated in order to describe the transformations. Yeah.
Okay, thank you very much.
Is there any other question?
Just a short comment back to the question by Professor Rizanov. The one way to address the important question that you raised is to see whether the presentation can be reduced to primitive axioms, and then of course the connection with category will be easier. I don't know whether it makes sense, but
yeah. No, sorry. Also, I don't know. But if, well, I see that I have still 10 minutes. So I will profit of this question in order to discuss with you, Professor, about your talk. I saw that very interesting your talk about the possible solution of IPR paradox, but I wondered whether it is connected with the probabilistic point of view of Bell inequalities. And I have seen that whenever you have a phenomenon and you consider the measurements, the possible measurements as random variables, in a mathematical model, you are estimating basically the distribution of these random variables, the distribution probability of these random variables. And this is done a priori. But after that, when you make a measurement, you are estimating the distribution probabilities a posteriori. So I wonder whether the measurement to take a measures of a phenomenon can be separated in this a priori approach and a posteriori approach. Is it worth to consider this kind of problems? Professor Santilli?
Oh, that's okay. I didn't know the question was addressed to me. Thank you. This is the question of the issue of measurements are now in very rapid evolution because Bell's inequality has been confirmed mathematically, theoretically, and also experimentally, but only for a point when referring to point particles acting in vacuum under very weak entanglement. Whenever the conditions are such that the entanglement becomes significant, then first of all, Bell's inequality are inapplicable. They are not violated. They are inapplicable because Bell's inequality is based on quantum mechanics, so it's only valid when you have a linear, local, and potential interactions. The moment you have a deep entanglement, you have non-linear, non-local, and non-potential. You cannot even formulate the Bell's inequality. Additionally, you correctly indicated that the measurement is ultimately calculated posteriori. It's correct. Everything you said is correct. But this is based on Heisenberg uncertainty. But now it is virtually been proved, published in highly referee, extremely severe journal. This was part of our 2020 conference on DPR. That when we have deep entanglement, then Heisenberg uncertainty are progressively weakened by progressively recovering Einstein determinism with increase of the density of the medium. So we start by apparently experimentally verifiable condition on the structure of a hadron. Then we pass the nuclear. We have an increase in density and the weakness of the. And then we go all the way to the gravitational collapse. If you remember the isotopic element that I presented, the isotopic element is the Schwarzschild at the limit of the high density is the Schwarzschild metric multiplied by the Minkowski metric, but the gravitational part is contained there. So therefore, on those limits, you recover Einstein determinism fully. That's our knowledge at this moment. Back to the question of measurement. So it all boils down. There are this is going now under significant revision, not by me. I'm not an expert in the field, but I have a number of colleagues that they keep me informed. But basically, it boils down to this to the so-called density of the entanglement, which is a new notion in the field.
Okay.
The speaker, I think that the presentation by the speaker was very interesting, and in my opinion, can be entirely word by word can be completed in our language, reformulated on an isospaces over isofield, where you can see the entanglement measure. You'll see that the isotopic element appear in any product, and the isotopic elements represent quantitatively the entanglement. So. And so that basically you have the foundation of what maybe one day what I've tentatively suggested to be called an EPR computer with deep entanglement. I think you do have a formulation. It's essentially there. Okay. And
thank you very much, Professor Heather.
Professor Heather.
Yes, I doubt this about Bell because the proof is not constructive, it's also local. You need a constructive proof to say it's mathematically proved.
Okay. Are there any other questions or comments?
Se ve la mano levantada de Michael Hitter.
Sorry, I should have put my hand down.
Okay, so thank you very much for the kind attention.
Thank you very
And we
much
may
for your
proceed to the
presentation.
conference.
Next speaker then.
Let me.
Next speaker is Valentina Rizanov.
Yeah, I was about to introduce her.
Yes.
Excuse me, Professor Santilli, because this is a new block of a conference. Then now Professor Guillermo Morales Luna is going to be the chairman of this section.
Oh, absolutely. Very well. I'm sorry, I apologize. I had no intention of interfering.
Don't worry. But then now.
But I want to allow me to introduce the First Lady, Italian style, in Italian, if I may. È un piacere presentarvi la gentile professoressa Valentina Rizanov for a beautiful talk, a bellissima lecture intitolata Approximately Computable Structures. Professor Rizanov, please proceed. I'm sorry if I usurped your presentation.
Sorry.
Okay, thank you for the invitation. Can you hear me?
Yes.
Thank you for the invitation and for the introduction. My lecture is dedicated to the memory of Zbigniew Gorziewicz, a dear friend who I've known for the last 10 years. And I kept meeting him and getting together with him at various conferences. But he has also visited the math department of the George Washington University and gave and spoke in our joint logic topology seminar. So Zbigniew was kind, friendly, gentle, generous. He was inquisitive, knowledgeable, enthusiastic, passionate, persistent, hardworking, dedicated, funny, memorable, revolutionary, fierce debater. And he was interested in everything related to physics or mathematics and many other things. So one of his interests was also computability and computation. And my talk will be in the mathematical theory of computability. And I will go through the background and at the end present some of very recent results, which are joint with Wesley Calvert and Doug Sensor. Perhaps the most important paper in the mathematical theory of computability was Alan Turing's 1936 paper on computable numbers with an application to the Entscheidungsproblem, decision problem. So it is in this paper that he introduced an abstract mathematical machine, so without regard for physical limitations. This machine had finitely many states that moved from one to another, had a precise finite set of rules given by a finite table, like a program, a finite set of instructions, and involved finitely many symbols. At any particular point, there will be only finite portion of the Turing tape, which imitated a piece of paper. There will be only finitely many symbols involved on the tape. And the states were supposed to mimic the way the brain moves from one mode to another. What was very important here is that he gave a negative answer to a decision problem. Because giving algorithms was nothing new in mathematics. Almost all of mathematics was algorithmic since Euclid, because you could intuitively explain to people what an algorithm is by just giving a set of some kind of prescription or a mechanical method. Showing that something cannot be solved by any possible algorithm involves knowing what exactly the algorithm is. And it wasn't until 1936 that it was clearly established what an algorithm is. So the intuitive notion of what an effectively computable function is, or a decidable problem that it represents. So effectively computable function is now identified with that of a Turing computable function. So we have an intuitive notion identified with an exact notion, which Turing introduced. And that belief is known as Church-Turing's thesis in computability theory and has been modified in complexity theory to polynomial and polynomial in quantum time algorithms and so on. So that means that we don't to show that something is effectively computable, we don't always write the Turing code, but we just intuitively explain how the algorithm works. And in all of the cases so far, it was possible to write such a Turing code, which could be very complicated. Also, there were several other definitions that follow Turing's definition of computability, and they all involving recursive functions, Chomsky's languages, Diophantine sets, and so on, Markov's algorithms, and they all turn out to be equivalent, which just reinforces this Church-Turing's thesis, which is the premise of the field. Turing also introduced in his dissertation, which was in 1938 at Princeton under Alonzo Church, in his dissertation, he talked about Turing machines which are augmented with so-called oracles. He didn't develop a very detailed theory of that, but the notion was there. So an oracle is a non-mechanical, non-algorithmic step in a computation. So an oracle supplies additional information on demand. And so the Turing machine computation every single Turing machine computation can stop from time to time and ask Oracle several questions. Usually, does this number belong to you if it's coded by a set? So it does have finitely many non-mechanical steps. So this is relative computability, relative to the Oracle, for which we may not have an algorithm to compute its membership. However, oracles allow us to introduce fine classification of subsets of natural numbers on N and mathematical objects and problems these sets encode. So this is a Gödel's idea to encode everything by natural numbers. So we can talk about natural numbers, but in fact, we're talking about arbitrary algorithms. So this leads us to the notion of Turing degrees, which Emil Post, one of the founders of computability theory, introduced in 1948, but even earlier in 1944 paper of Emil Post, there's some hints of introducing this notion. So we have two sets of natural numbers, A and B, and we say that A is Turing reducible to B, or the Turing degree of A is less or equal than the Turing degree of B, if A can be computed by a Turing machine with Oracle B. So A is B computable. And so this is an order relation, and we can define an equivalence relation that A and B have the same Turing degree or they're Turing equivalent if A can be reduced to B and B can be reduced to A. We also say that A is strictly below B, strictly Turing reducible to B, if A can be computed by a Turing machine with Oracle B, but not vice versa. B cannot be computed from A. Another possibility for two sets and two problems they encode is that they have incomparable Turing degrees. Those are harder to build. So we can easily show that any two Turing degrees have supremum. So we have two sets, A and B, and we define a join A join B by multiplying elements from A by 2 and elements from B by 2n and adding 1. So we're using even and odd numbers to kind of separate A and B. Now we can show that the degree of A join B is exactly the least upper bound for A and B. So this shows how Turing reducibility works in an easy example. For example, A is Turing reducible to A join B because given an input n, a natural number n, we can decide whether it belongs to A by multiplying it by 2 and then asking Oracle for A join B. Does this element, which is now 2n, belong to you? If yes, then yes. If no, then no. It is much harder to show that there are Turing degrees for which there is no infimum. No, so therefore we have a partially ordered set of Turing degrees of complexity, which form an upper semilattice. So it's a very rich structure. So in this upper semilattice, all the computable sets have Turing degree 0. So what are computable sets? Those are ones that can be computed by Turing machines with no oracles, by autonomous Turing machines. More precisely, the characteristic functions are computable functions. And the characteristic function is defined for a set S, is defined to be 1 if n belongs to S, and 0 if n doesn't belong to S. So it's reduced to a decision problem, to a yes-no problem. So the complexity theory in computer science happens within this Turing degree 0, because it's also, there are many ways in which a set can be algorithmic, can be computed with various time and space resources and classified in many other ways. In computability theory, we use algorithms to study non-algorithmic sets, but through the notion of relative computability, which is captured by Turing degrees. There are also other degrees of complexity. So there are uncountably many Turing degrees. There continue many Turing degrees, as many as there are sets of natural numbers. We can see that because Turing machines can be algorithmically enumerated as M0, M1, M2, and so on. We always start with 0 in logic, so. They can be algorithmically enumerated because each Turing machine is a finite set of instructions. And so we can, and each instruction is a finite set of symbols involving symbols on the tape and states. If we fix an oracle X, additional information for our computation, we can also algorithmically enumerate Turing machines with oracle X. So there are only countably many of them. And because these are all X computable sets, they're countably many, exactly infinitely countably many sets in every Turing degree. Because we can change set but finite information and can still have the same degree. So one interesting thing that appears from the very beginning of formalizing computation is that a Turing machine may not halt on an input n. It may compute forever. So even if we just want to study total functions, totally algorithmic functions, we are forced to consider this halting problem. And it turned out that halting problem is undecidable. So we say that the Turing machine M computes a partial computable function. And because we don't know whether it will halt always or not. And so the domain of that partial computable function is a subset of n. Could be a proper subset or could be all of n. If the domain is all of n, then we have a total computable function, or we simply call it a computable function. So we can, partial computable functions can be algorithmically enumerated as phi0, phi1, phi2, and so on, because we managed to algorithmically enumerate by doing this careful Gödel coding all the Turing machine or Turing machine programs. However, here we have a lot of repetition because Turing machines are syntactic objects. By Turing machine, we assume Turing machine program, but also universal Turing machine. So here I'm using them as programs. So then syntactic objects, so we can enumerate them while crossing the repetitions, but then different algorithms can compute the same functions. So we have a lot of repetitions in this list. But all our partial computable functions are here. And it's an algorithmic enumeration. So we also, it's algorithmic, not just with regard to input, but also to the place this function occupies in this list. So some of these partial computable functions are total. So this list contains all the total computable functions. And some of them are 0, 1 functions, and therefore computable characteristic functions, and they represent computable sets. We cannot algorithmically enumerate computable functions. Those are total partial computable or total computable functions by using a simple diagonal argument, one of these Cantor's arguments. If we had an algorithmic list, but it's algorithmic, F0, F1, F2, and so on, then we can define a function Fn on n plus 1, and it will be computable because the list is computable with respect to also the place the function has in the list. But it's not equal to any of the functions on the list, so we add a new function. Now this trick will not work with partial computable functions because both could be undefined. So undefined plus 1 is the same as undefined. So the halting set is not decidable, and it's represented by a non-computable set. So the binary relation Kn, where K is the kth Turing machine and N is the input. So such that mk holds on input m is not computable. We can make this even simpler. We can just take the same, that k to be equal n, so it's kind of diagonal here. So the set is a famous halting set H, which is the set of all n such that mn holds on input n. This set is also not computable. In fact, these two sets are Turing equivalent, so we might as well deal with a set which is just a subset of n. So it's not computable. The Turing degree of this set is denoted by zero jump. And we can show that zero is strictly below zero jump. So we have a strictly higher Turing degree. Now this idea can be extended to any set X used as an oracle. So we can define the halting set with oracle X. So there will be just, and we get this set, we call this set X jump or X prime. So it's a halting set, but now we can use X as an oracle. And what happens is, for a degree X, Turing degree X, which is degree of the set X, we get a strictly bigger degree, which is Turing degree of X prime of the halting set. So with each Turing degree, we get this infinite chain of increasing Turing degrees. So for the computable sets, 0, then we get zero jump, the degree of the halting set, then we can use zero jump as new oracle, get zero double jump, and so on. We can continue ad infinitum. So within this partially ordered structure of Turing degrees, we have all of these infinite chains for each Turing degree. So what kind of set is a halting set? So this set H, set of all m such that mn holds on input n. Well, it is a computably enumerable set. So those are sets that are very close to computable sets, but they don't have to be computable. So, so these are sets where the algorithm will halt if there is an answer, or may compute forever, but we really don't know at any point whether it's going to go on forever or it will halt in some future point. And such sets are called computably enumerable or algorithmically enumerable because we can enumerate them by an algorithm. So here we can enumerate this set by simultaneously running all the Turing machines. What does it mean simultaneously running? That means at each step we run finitely many of them on finitely many inputs. We keep increasing the number of Turing machines we have and the number of inputs because it has to be algorithmic. And whenever some Turing machine halts on input n, then we enumerate it in this set. If it doesn't, we keep computing by adding more steps and more Turing machines. So a computably enumerable set is the range of a computable function. It's a range of an algorithm. We can also replace this by a partial computable function. Of course, it'll be another function. Every total computable function is partial computable, but if it's enumerated by a partial computable function, we can transform it to another total computable function. And a set is computably enumerable exactly when it's the domain of a partial computable function. So when there is a single algorithm, so that is exactly the halting set for that particular algorithm, because that's what the domain is. It's a halting set for that particular function. And a lot of problems that turn out to be undecidable in the important problem in the history of mathematics, like the word problems for groups and other similar problems, and Hilbert's 10 problem, they turn out to be computably enumerable. So computably enumerable sets can also be algorithmically enumerated because we had algorithmic enumeration of all the Turing machines and therefore partial functions they compute, and therefore the domains of these partial functions that are computed by Turing machines. And the domains of partial computable functions are exactly the computably enumerable sets. So we have an algorithmic enumeration of computably enumerable sets, and some of these computably enumerable sets are computable. So how do we distinguish computable sets among computably enumerable sets? Well, those are ones where enumeration is in the increasing order, because for computably enumerable set, the enumeration doesn't have to be in the increasing order. But if it's in the increasing order, then we'll know at some point that something is not enumerated. Another way to identify computable sets from computably enumerable are that they have computably enumerable complements. So in that case, we can enumerate both set and the complement, so we'll for sure know whether an element is in the set or not. But the computably enumerable sets that do not have computably enumerable complements are not computable. So the complement of this set, the set of all n where m of n doesn't hold on input n, is not even computably enumerable. Computably enumerable sets are all bounded by zero jump. So in some sense, the halting set is the most complicated. We use the term complete computably enumerable set. However, there are infinitely many Turing degrees in this structure, and that's also an interesting structure. But it's a countable substructure of the structure of Turing degrees. So the partial computable functions can be used to approximate algorithms. So in a lot of problems in mathematics, in particular in combinatorial group theory, the researchers wonder whether it is worthwhile to distinguish which results depend on special and potentially rare inputs and which don't. So when we say that the word problem for groups is undecidable, we're thinking of particular very complicated groups. But what about other groups? Maybe in a lot of these cases, they can be solved. So we're here taking the worst possible example in a family of structures to talk about complexity of some problem. So in particular for problems on groups, researchers propose to use the notion of density to investigate whether a particular computable function could solve almost all instances of a problem. So we're talking here about approximate algorithms, not exact algorithms. And these kind of algorithms have been used a lot, probabilistic algorithms and so on. But the mathematical theory of this has been developed relatively recently. In particular, a number of researchers who work in combinatorial group theory, where we have a group given by relations and by generators, they show that for a large class of finitely generated groups, the classical decision problems, such as the word problem, the conjugacy problem, and so on, not that they're undecidable in computability theory, but if we allow this approximate algorithm, they are simple. They have even linear time generic complexity for these algorithms. In particular, a finitely presented group with the undecidable word problem, which was given by Boone. So the word problem was posed by Dan in 1970, and then it took a very long time to show that it's undecidable. Was obtained by Novikov and Boone independently. But the finitely presented group, the counterexample that establishes undecidable word problem, here is very simple. It has a generically computable copy. So in a paper in the 2012, Carl Jakush, a logician, and Paul Schupp, a group theorist, extended this approach to a broader context in computability theory. So they introduced these studied generically computable and coarsely computable sets of natural numbers. That's what they named them. So very recently, together with Wesley Calvert and Doug Sensor, we worked on generalizing these notions from sets to arbitrary algebraic structures by defining generically computable and coarsely computable structures. And we also defined further refinements of these notions. So what is asymptotic density? So for a set D of natural numbers and any natural number n, the density of a set D denoted by rho n of D is just the number of elements. So this denotes the number of elements, the cardinality of the first n elements of natural numbers which belong to D divided by n. So it's just this quotient, how many of the elements among 0 up to n minus 1 are in D divided by n. So the asymptotic density of D is the limit of rho n of d if it exists. So for example, if we take a set 2 to the n, then that set has density 0. It's possible to show that. We say that set is asymptotically dense or simply dense in this talk if its density is 1. So Jacques-Shop used this notion of density to approximate computable sets and introduced the notion. They introduced two notions. So the first notion is a generically computable. A set of natural numbers is generically computable if there is a partial computable function, 0, 1 function, such that its domain has density 1. And on its domain, it approximates the set S. So what we have here that on some elements of S, we may not have an answer because this is a partial computable function. But on a large set, a set of density 1, we have a partial computable function that holds at that and its domain and exactly computes the set S. There's another notion, and the two turn out to be incomparable, is of a coarsely computable. Here we always have an algorithm. So set S is coarsely computable if there is a total computable function tau, but it doesn't have to always agree with S. So it's always defined, it's a total computable function, but the set of elements in which agrees with tau has density 1. So this is equivalent having a computable set given by this function tau, such that the difference between S and tau has density 0. So in one case, we may not know the answer, and in the second case, the answers may be wrong, but correct things happens on a dense set. So what we did is attempted to generalize this notion from sets to structure. Here an important notion is that of a computable structure. And we'll restrict to finite language. Finite language is the operations and relations our structure has. So a structure D is computable if its domain is computable. We can even assume natural numbers if it's infinite. And each relation and function is computable. So if we have a group, the group operation has to be computable. Then it will turn out the inverse operation is computable and so on. All finite structures are, of course, computable. A theorem of Rabin says that a finitely generated group has a computable copy. By copy, we mean isomorphic copy, exactly when the word problem for that group is decidable. This is our definition. A structure D for a finite language is computably enumerable if its domain is now computably enumerable. Each relation, if it has relations, is computably enumerable. And if it has functions or operations, then each function is the restriction of a partial computable function to D. So it has to be defined on D, but it's a restriction of some partial computable function. So we define generically and coarsely computable structures, which we call dense structures. And we showed that there are two directions which these notions can potentially trivialize. Either all structures have a densely computable copy, or only those with a computable or computably enumerable copy. So trivialize in a nice sense. And we have further introduced a graded family of sigma, so-called sigma n conditions for substructures, in which we require that the dense sets under consideration are strong substructures of the original structure, because we wanted these notions to be structural. And for each family of structures we investigated, there was some natural number n, such at that level, the notion of density relative to sigma n trivializes in the above two directions. So, but what should be the right definition for a structure? For example, what if we have a binary relation? Then we have to look at the density. If D is a subset of natural numbers that has density delta in n, then D cross D, its Cartesian product, has density delta square in n cross n. So if D is dense in n, then D cross D or D square is dense in n square. However, we constructed a computable dense set such that for any infinite computably enumerable set, the product, this square E cross E, is not a subset of C. So we have to be careful not to take subsets of n cross n or whatever our relations, arity of our relations is, but to look for this squares to be contained. So this is our definition of a generic computable structure. Again, we have finite language. we assume the domain is N. We're dealing with countable structures. We may have functions Fi of arity Pi, relations Rj of arity Rj, so binary, ternary, and so on. So we define A to be generically computable if it has a substructure D, which has computably enumerable domain of asymptotic density 1. And they're partial computable functions, phi and psi j, that approximate functions and relations in the structure, but phi has to agree with fj on d to the pi. So this Cartesian product of this dimension. And similarly for partial computable functions that approximate relations in our structure. And this is a true generalization of the previous notions for sets, because out of each set we can make a unary relation structure natural numbers by taking n and that set S. And then we show it follows that M as a structure is generically computable if and only if as a set is generically computable. There are some surprising properties. Commonly studied structures in logic are equivalence structures where we have a set with a single equivalence relation. And a lot of relations in mathematics are equivalence relations. And these structures look simple, but they do have a complicated computability theoretic properties. But we showed that every equivalence structure has a generically computable copy. That was an unexpected result. Another group of results we obtained was for, we call them injection structures because injection is one-to-one in mathematics. So these are structures with a unary function on the domain such that that function is one-to-one. And we showed that an injection structure has a generically computable copy if and only if A has an infinite substructure isomorphic to the computable structure. So kind of close to the computable structure. But, and there are other characterizations. But for example, injection structure has a sigma 1 generically computably enumerable copy if and only if has a computable copy. And we considered other families of graphs and structures with, where we'll look at this sigma and complexity. So we also defined a coarsely computable structure as a computable so A is a coarsely computable structure if there is an extension of A, E, if there is a computable structure E, which is extension of a substructure of A. So A has a substructure D, D is part of A, the domain of D is a dense subset of the domain of A, and D can also be extended to computable structure E, so that when we restrict structures A and E on D, we get the right structure D. So the relations and functions extend the same way on D. So here we're approximating a dense substructure of A by a computable structure. And turn out this is a good definition in terms that extends what's known for sets, because again, if our structure with a unary relation NS is coarsely computable, if and only if S is a coarsely computable set in the sense of Jokic and Shop. And we had many other technical results, even for equivalent structures and one-to-one functional structures, which could also be viewed as directed graphs with only one arrow pointing to each node. For example, we show that there is a generically computable structure that is not coarsely computable. That was true for sets, so it follows from this analogy with sets. And there is a coarsely computable structure that is not generically computable, and so on.
Okay.
And thank you. And these are the references. So one paper is going to appear soon, and we're working on the other paper. We're dealing with computable isomorphisms. Thank you.
Thank you very much. We have a question from the chat. Professor Heder asks, what do you mean by undecidable? If in the Gödel sense, it is only valid locally.
So a problem is decidable, some problem or set or an object, if there is an algorithm which works for every input, for every instance of that problem. So when you input any instance of a problem, say it's a decision problem, then the algorithm will give you answer yes or no. So undecidable is a negation of that. So no algorithm will work for all the instances of a problem. So you're always looking for the worst possible cases to put a maximum bound on the complexity of that set.
Okay, thank you. I have a question.
Hilbert's 10 problem is undecidable. So there is no algorithm such that when you input a Diophantine equation, the algorithm will tell you, yes, it has solution in integers, or no, it doesn't have solutions in integers. For rational numbers, we don't know. That's a big open question.
Okay, thank you very much. I have a question by myself. In cryptography, in security, in the calls, one may take an NP hard problem, and the instances of the problem may be taken as public keys, and the solution of that problem is taken as the private key. So in order to identify, to impersonate the owner, one intruder should solve the problem. But it happens that most of NP problems are generically easily to solve. So the problem is to find really hard instances of NP hard problems. Have you dealt with this problem? Have you tried this problem?
So when we define this, say, completeness, like NP complete problems, right? Yeah. So we are looking for the worst, for the most difficult problems in that class. That means that it's complete if every instance of that problem in that particular class can be reduced to that problem. And if you find one such hard problem and then reduce that problem to another problem, then the new problem has to be hard because all the instances of the problem in that class can be reduced to it. So this is kind of the opposite of that. And we have a notion of completeness like that in mathematics, where the reduction just is computable. It doesn't have to be polynomial time or efficient in any way. And so we're looking for the worst possible problems. But this is the opposite. This is looking for where most of the problem is looking at the density conditions and approximations, like maybe there are a few hard problems or some problems, but how many of them are hard and how many of them are majority problems still doable.
Okay, thank you very much. Are there any other questions or comments?
Yes,
Well,
maybe comment, if I can, maybe comment,
yeah,
not related exactly to the talk, but just historical, maybe interesting thing. In 2006, in February 2006, we invited Zbyszek to give seminar with Valentina and me at George Washington University, and Zbyszek gave very interesting talk about bladed logic. So this is still, I think he published finally something about bladed logics, but it's the topic which is really worth of considering. And in particular, one slogan was set theoretical Young-Baxter operator in this blading logic. Thanks.
Thank you very much. Any other question or comment? Well, if not, we thank again Professor Valentina for her very interesting talk, and we go to the next speaker. The next speaker is Professor Francisco Hernández Quirós from the Facultad de Ciencias of UNAM. Francisco, are you ready?
Yes, I am.
So please go ahead.
Yeah, my camera is working, I think. And is my mic working? I think it is also working. Okay, yeah. So I can start right now. Okay, thank you very much for attending this talk. Let me just...
we do not see anything.
Oh, don't worry. You cannot see anything? Okay, I will start presenting. Just a moment.
Also, I have a weak reception of the voice.
Okay, let me adjust my mic. How is now?
Oh, it's too loud.
Too loud? Okay.
Yes.
And now?
It's okay.
Is that okay?
Okay.
Okay, perfect. Perfect. Okay. Sorry. And now let me present my talk. Now it's.
Now we see your
Okay.
desktop.
Okay, perfect. I think, are you looking at the whole of my desktop or just my presentation?
As you please.
Yeah, okay.
Well, the
So,
presentation is, excuse me, the presentation is very small.
Very small. Okay, let me make it in the whole. Okay, what about now?
Now it's okay.
Okay, thanks. Okay, okay, the presentation is called A Balance Between Cumulative Knowledge and...
It's too big.
Sorry?
Decrease it a little bit so we can read.
Ah, the presentation is too big?
It was too wide, yes, at least for me.
Okay. What about this? Is this okay?
Yes, that is much more, it's not center, but it is more visible.
Okay, so I don't know what is happening. But is it readable?
Yeah, much better now, yes, indeed, yes.
I thought you could make it bigger, but perhaps everybody has a different screen setting.
Yes.
I still see
maybe
parts
it's the
of the
case.
bird.
Yeah.
Okay, so let me try again. I'm going to do it in the, okay, whole screen is okay?
A little bit bigger, I think it should be.
It's very fine for me.
Okay, I'll carry on. Anyway, I can send the presentation if anybody wants to have a look at it later. Okay, so I was telling that the title of the presentation is A Balance Between Cumulative Knowledge and the Speed of Proofs in Propositional Calculus. And it's based on a paper we published last year. The main authors are Santiago Orozco, Tosenil Bibitsik, and myself. And but before I start with it, I would like to say a few words about Zbigniew. Zbigniew, everybody has talked about him. I think I cannot add anything to it. Just to say that I'd met him in 2004. He invited me to participate in the second Graph Operant Logic Symposium that he used to organize every year. And it was very generous of him because he didn't know me. And he said, no, it doesn't matter if I don't know your work. I think it's going to be of interest to everybody. So I was invited. I gave a couple of talks in that series of seminars. I couldn't attend further seminars, unfortunately, but I was about 2 or 3 times, I think. And what I have to say is that people like Zbigniew is what make science tick. That's the kind of people we need. People who are energetic, open to new ideas, and willing to hear to people that are not heard normally. So I'm very, very much in depth with him, and so I go to my talk now. Okay. So the main point of this paper was to not to look for better ways of proving theorems, because there are very, very good automatic theorem provers. But rather than that, we were thinking of how humans used to learn how to prove logic, and to see if there was something common to the way computers prove theorems. So we were thinking of the typical logic student that when he's learning to prove theorems, he normally does it from scratch. But later on, he's able to use previously proved theorems in order to either shorten or facilitate proofs. But after a while, he stops doing this, or she stops doing this, because there are too many theorems proved already. So we thought, okay, this has to be with the size of the database of previously proved theorems. So there is a way of organizing this information so that humans and computers can use it more efficiently. And our guess was that there was no way of doing this. And we ran very soon into difficulties trying to understand how to store and recover information in a database like this. So this is very similar to what happens in optimization theory, where people have found what they call no free lunch theorems. Theorems where you have a method that seems to work very well for small examples, but as soon as examples start growing in size, you find out that the method is no longer working efficiently. And at the end of the day, it's probably better to introduce a brute force algorithm to get results. It can be as inefficient at that as a brute force algorithm. So we found out that this happens also in logic. We also found that there is a kind of phase transition here where before a certain size of problems, everything works fine. And after that, everything stops working. But we have been unable to pinpoint exactly how this phase transition behaves. And that's what we're trying to do in the future. So in this paper I was talking about, we just presented a series of simulations. And now and the rest of the team are involved in finding a good way of formalizing this, presenting this even in a kind of a new free lunch theorem, and also to see if this information can give us better hints of how to store and recover information in logic. Okay, so everybody knows this, what I'm going to say in this page, that classical propositional calculus is a nice logical system because of its decidability. But nevertheless, decidability is not everything, because many of these problems are very costly computationally speaking, and also everybody knows this. Satisfiability, for example, is say the classical NP complete problem. Verification for tautologies, for example, is also a very important problem, and is in co-NP. And finding the shortest proof of the theorem is NP hard. We don't know exactly where in the polynomial hierarchy is, but everybody suspects it's very high in the hierarchy. It has to be much more difficult than SAT and TAP. So the point is, this decidability is not everything, and human beings, even having these decidable algorithms, cannot do things very efficiently. So normally what they are given is a series of rules in a formal system, natural deduction, Lukasiewicz, whatever you want. And after a while, after they are trying to learn how to prove theorems, they discover, or they are told, to use previously proved theorems in order to speed or facilitate demonstrations. Classical theorems for this are the Morgan laws, for example, hypothetical syllogism, the theorem of double negation, etc. And what they do is to use these new theorems to prove another a batch of new theorems. And after a while, they have gathered quite a big amount of theorems, and repeat the process until at a certain point it's more difficult to look at the list and say, okay, this is going to be useful or it's not going to be useful. So they go back to their initial method, that is trying from scratch to prove something. So is this only human? I mean, this is a human behavior, or is a more general phenomenon? Computers would be better off doing something else, or they should do as humans do. So we wonder how it could be the case with very long sets of theorems, and we did some simulations to see what happened. We found that the efficiency of a theorem prover is that is forced to accumulate theorems degrades as more theorems are added, and we expected that, of course. What we didn't expect to find was that this degradation happens very soon and very fast, much sooner than we expected. So computers are not much better than human beings for this. I mean, they are, but not in a significant way. And also, and this is very surprising, we also found that the automatic theorem provers that we were using not only were slow in producing proofs, but also those proofs sometimes were even longer than proofs tried from scratch. I mean, what I mean by this, I mean, if they had not given previous information, previous theorems, probably they would find a shorter proof in a shorter time. Okay, what we use for this? We use two very popular theorem provers. One is prover 9 and the other is Approach. We use prover 9 because of this resolution method, and Approach because it's natural deduction. We thought these are two very, very different approaches. And resolution tends to be not very easily understandable for a human being, like Approach is, natural deduction is very, as its name says, very intuitive. So we produce thousands of tautologies with using a systematic approach, and then feed these provers with some of these tautologies as additional axioms of a system. Of course, these axioms were not needed because tautologies can be proved from scratch with these two methods. But we give them the provers this in order to see if with previous accumulated information they will proceed to give us faster proofs or shorter proofs. And what we found out is that they don't do that. For example, I got here the results with prover 9. We performed 15 experiments using prover 9. This is just a selection of these experiments. For example, here in the table, experiment number 11, we used 5,400 proofs, and the cases where the prover managed to do a faster proof were just 606, which is a very low percentage. But there was also 94 cases where prover 9 took longer time or produced longer proofs using this information, these additional axioms we gave it. And the ratio between these two, as you can see, is not very low. It's relatively high, but it's still not a very high number. That means that in a significant proportion of cases, it's counterproductive to give the system this kind of additional actions and axioms. And the rest of the experiments produce very, very similar results. You can see this. Experiment 10 is roughly the same. Experiment 7, it's even a lower case of positive improvements. As the same goes for experiment 5 and 3. So this is a very, very low, very few cases of improvements in the automatic theorem provers. We also did this small graphic as a way of representing the same information. In this graphic, you can see not as a percentage, but as a gray area where there was a case of certain improvement. As you can imagine this as a huge matrix of tautologies, candidates for theorems of a prover, and in each column we were giving it additional axioms in order to see the system would improve in performance. And as you can see, it's a very sparse matrix. In very few cases there was improvement. So the point is, and I probably should go back to the previous case, is that these cases are very exhaustive, and it is the case because we are using very small formulas. Tautology is very, very simple. The kind of P implies that Q implies P, that kind of things. Nothing very sophisticated. So the system becomes inefficient with the smallest of formulas. You don't need to go very, very far to find this. And it doesn't have to do with the power computer. The idea is that this result would be attained with any computer you use, because what we were looking was not an absolute speed, but speed compared with the speed the system would give you if you gave just the tautology without any additional axioms. Also, about approach gave us very, very similar results. Here they're presented in a different way. You can see this kind of small steps like a staircase. And in these staircases, like figures, gray areas are areas where we didn't see any improvement. Blue areas are areas where, or cases where we see some improvement. And red cases are cases where you see a degradation of performance instead of improvement. Most of the blue cases, as you can see, are in these diagonals, the top of the steps in the staircase. And those are trivial improvements. It's where you receive as an axiom the tautology you are trying to prove. So if you take that into account, the amount of positive cases is even smaller. It's very, very, very rare to see improvement. So approach in the same way as Prover 9 was unable to produce significant amount of improvements in the proof of theorems if you give it more axioms. And by axioms, I mean, of course, this accumulated amount of previous theorems. So this is a very, very bad result. We were trying to find an explanation for this, and it was still trying to work out a formal explanation. But what we found, and you can have a look at the paper, you want to see the details, is that when you put these constraints impose these constraints on an automatic theorem prover, that it has to use previously proved theorems, and it has to try to improve the proof, the demonstration with this, is going to get clocked very easily, very soon, and the accumulated knowledge becomes a hindrance instead of an asset. And an automatic theorem proof that is able not to get clocked but improve performance. We call it normal. Probably the word is not very, very fortunate. Another one can be used, but the idea is that more information allows it to improve. It's a very, very difficult constraint, and it's very difficult to find. Also, as I said, we also find that some proofs were longer, and we wondered what is happening there. Why these systems are made in order to find the fastest proof, and this fastest proof probably imposes some constraints that makes it look for more steps instead of shorter or less steps. And remember that steps in the formal demonstration, of course, is just a final photography of the result. The search for these steps is much bigger. And this can be ascertained partially with these theorem provers because they don't give you the total information of what happened while looking for the proof, but you can see a partial trees of the search. And of course, in these cases, the search becomes shorter if they introduce additional steps. But in that case, the shortening in time is not proportionate to the lengthening of the demonstration. So this is a very, very strange result. And the idea is that after a while, brute force is better. It's a better approach for proving a theorem, which is a very disappointing result. Well, what are we trying to do now? We are trying to find, as I said, a no free lunch theorem for this, stating that when you are trying to optimize proofs in the way that a naive approach would lead you to do, the result is going to be worse very, very, very soon. So how can we do this? Our idea is a very, say, probably maverick idea to use algorithmic information theory to do this. Our suspicion is that the theorems that really allow you to shorten a demonstration are theorems that have very high information, very high value in a way, in a certain way. And we are trying to characterize this value using Kolmogorov's algorithmic information theory. And if we manage to do this, the next step would be to try if increasing this value also allows us to shorten the proof and to organize better the information we get by proving theorems. If that's the case, we would be able to formalize the notion, prove where exactly what the requirements are for a valuable theorem, and then probably to be able to pinpoint where exactly this phase transition lays. And in that way, probably we would be able to also suggest heuristic methods that may not be as fast as brute force but exhaustive search algorithm, but they can be faster, probably at the expense of certain errors that may be tolerable. Okay, so as I said, we are trying to characterize the informational value of these theorems using Kolmogorov theory, well, when we got this ready, I hope I will be able to tell everybody who is interested about it. My email is in the presentation. If anybody wants to communicate with me in the future, and that's it. These are some of the references we use for our work. Any questions, comments?
I have a question. Is it okay? Do you think your system can be adjusted to have some context? For instance, proving theorems of geometry, or at least projective geometry?
I see. Well, it depends very much on the kind of logic that you want to use. We use proportional calculus because it's a decidable theory. But of course, these ideas can be extended to any decidable theory. You have undecidability, automatically is beyond what we are interested in. Not that it's not interesting, but it's not what we are investigating. But I don't know, I suppose geometry, as far as I know, there is a subset of it that is decidable, and in the predicate calculus. So I suppose it can be done with that, yeah.
So maybe philosophical question. Could this system actually discover new theorems?
Oh, well, these systems work with an algorithm that they explore, not exhaustively. They try to use better strategies, but at the end they can be exhaustive. They try to discover how to prove things. For example, you want to prove P implies that Q implies P. That's a very easy theorem. Approach would try to use the syntactic structure of the theorem. What it would try to do is to prove it by introduction of implication, for example, because there are two implications are. And it's a very fruitful approach because that can be proved in probably four steps. So that's the way they try to do it. It's not that they are trying to produce random theorems. These systems work by you presenting them formulas and ask them to produce a proof, or to say they are not proof for that formula because it's not a tautology. Yeah.
I see. Thank you.
Okay, Lourdes del Carmen, por favor, please.
Thanks, Francisco. It's very interesting, your work. I work with theorem provers, but interactive theorem provers, not the automatical theorem provers. And I have a question. What about to separate or to organize the statements, the theorems or dilemmas you are trying to use in different databases, and then just choose some of the databases to limit the number of of statements that you are trying to use automatically to prove something.
Yeah, I mean that would be the first approach. And as a matter of fact, because we're using very small sets of axioms, you don't really need to organize much. That's probably what surprised us more of these results, that we just introduced, let's say, 10 additional axioms. And that's a very small set, as you can see.
Yeah.
And even a small set like that produces worse results. The system degrades very, very easily. So having more complex databases probably will produce an even worse degradation. The point is that if we knew how to organize this information in a way that is useful, of course, that would work very well. And when you are using these interactive theorem provers, like I suppose you are talking about Koch and the like,
yes.
Yeah, there's a human being doing that organization.
Yeah, of course.
Yes, and that human being knows what is important in the theory. And that human being can lead the system in order to have proper proofs and the like. So how can you capture that human being intuition? But also, human beings after a while also stop being effective. Is there a way of doing this automatically without human intervention that is scalable? That's a question. And we think that probably the answer is in Kolmogorov's algorithmic information theory. We managed to say, okay, this theorem has a lot of information, should be at the front of all the theorems that are going to be used to try to shorten a proof. That may work, but we don't know yet.
Yeah, in Koch, there are some tactics to prove automation. And these tactics, as far as I understand, they are simulating the same reasoning that is behind prover 9, or resolution in some at some level. These automatic tactics work with different databases, and probably that's why I am suggesting you can review this this approach in the Koch proof assistant, and then probably get some ideas from there. Thanks, Francisco.
Thanks for the suggestions. I'll have a look at it. Yeah, thank you.
Thank you very much. Professor Sobchik?
Yes, your talk, I enjoyed it very much. It reminds me of a talk I heard by Hangbo Lee, and also in line with Professor Kochik. He used projective geometry in Clifford algebra, and somehow was able to, by using the language of projective geometry, he could prove many results with one theorem in some technique that he developed for automatic theorem proving, which was very impressive. So I just thought I would bring that reference to Hangbo Lee's work, if you're familiar with that.
Thank you. Yes, yes. I'll take a note of it. I think the session is being recorded, so I have a look at what you said. And yeah, I have a look at it. Thank you.
Okay, thank you very much. So I don't see any more questions, so let's go to the next speaker. So please, Lourdes del Carmen González.
Okay, let me, I think you can stop my.
I think you should do it by yourself.
I'm
Yes,
trying to do
you need to
it.
stop sharing.
Yes, I'm not very good with Zoom, sorry. Okay, no, I think
From the staff, does anybody can anybody to stop sharing?
because it doesn't, okay, stop share. Yeah,
Okay.
Sorry, it's done.
Okay. Maybe this is okay for everyone. So, okay. Well, good afternoon in Mexico for everyone, and probably good evening for the other people. I'm Lourdes, and I am very pleased and very happy and honored to be here. I want to thank to the organizers the opportunity to share my work. I work in the Faculty of Science. Recently, I arrived to this School of Science at UNAM, and I'm going to talk about some work in progress with Professor Fabio Miranda and a student of the master's degree, Javier Enriquez. First of all, I want to say that unfortunately, I didn't meet in person Professor Osiewicz. I regret that I didn't have the opportunity to meet him at least in some of these conferences or workshops in Mexico. But now I am learning many things about him and the efforts he made to relate many areas, not just in mathematics or physics, but also with computer science. And that's why I choose to talk to you about this work. So this work is about the relation between computer science and category theory, something that we call the proof as programs methodology, where the type theory we use in computer science for describing types or the properties of programs could be used as a universal way to talk of computer science. Some kind of people or researchers or computer scientists, we are very compromised with the use of types or the type theory to program or to direct the programs we can obtain. But this is not all a isolated area, the type theory, but is two-way related with other fundamental theories in computer science and mathematics that are logic and also category theory. This is what some people call computational trinitarism. And here I quote the words of Robert Harper. As a computation can be manifested in three different forms: as propositions in the universe of logic or logics, types in the sense of programming languages and programs, and also as a mapping or function between structures. And these three aspects are very important to work with them, maybe isolated or let's say bidirectionally or three-directionally, I don't know how to say that, because all of them give many ideas or many different points of view of the same notion of computation. And this is what I'm going to talk about. This talk is directed by the categorical approach to functional programming, where some structures, categorical structures as coalgebras or algebras or coalgebras can be seen as data types or types, simply types. Also, the functions can be understood or can be seen from the categorical point of view as morphisms, or vice versa. It's just a correspondence, a clear correspondence. And all of this is based on the lambda calculus from Church and also from Turing and other mathematicians. Also, from the philosophical point of view, there are many efforts to have a correspondence with some notions of logic and languages within category theory. And this is a case of the Martin-Love type theory, or the dependent type theory, that can subsume many logics and then interpret these logics as some special type systems for functional programming, or just for languages in programming languages. So, for instance, one of the main systems used in functional programming as a foundational language to describe types and programs is System F. System F was developed by Girard in the 1980s, and John Reynolds and other people discover or just use this system to give a foundation for some programming languages, functional programming languages. This system allows us to describe types as the first category, the first definition, and also the corresponding terms for these types. We also include a notion of context to have local and global information about some terms or some programs. And this system allows us to manipulate sequence in the sense of natural deduction sequence, or the Gensen idea of sequence, where these three notions or these three aspects are related. We can assign, or we can give a type A to any term or any program in this system or in this language under some information given by the context. And this language is very helpful to model lambda calculus and to model functional programmings, or very many notions of computation. This system is accompanied by a set of typing rules to assign a type for any construction in this system, and also a set of rewriting rules in the sense of the theory of rewriting systems to define or to model a notion of computation, the operational semantics that allow us to compute the result of a given term or program. I will not focus in the second set of rules, but in the first. The first, this set of rules that allow us to give a type to a term, to any term, is syntax directed, as you can see. And the advantages of this system is that we can give a automatic or a decidable process to assign a type for any term. So modern programming languages or functional programming languages include the type systems as this set of rules to provide a type checking process for any program. So this is the side, the programming language side, and I will talk to you some of the ideas that make a correspondence from this side, the programming language side, to the categorical side. So in category theory, we have many constructions, but the main idea under this theory is to have structures or mathematical structures described by the relations within other objects or other structures. So we are going to consider a category that has products and coproducts, and also the distribution of products over coproducts. Also, we want to model some kinds of computations or some behavior, some computational behavior under the notion of functors. So, for example, we know that an F algebra in category C, maybe you can think about C, the category C, as a Cartesian closed category with all these characteristics. And the algebra, the F algebra designed by this functor, allow us to define the morphism between algebras. This diagram commutes, and then we can go either for downside or the other side, and we can define the composition of these arrows or these morphisms in order to have other behaviors. In particular, in category theory, we can take advantage of the duality principle, and of course, we can define the dual notion of algebra, that is an F coalgebra. We can just turn around the arrows in the diagrams, and the diagram still commutes. These notions of algebra and conalgebras are the basic ideas to recover or to interpret or to give a categorical interpretation of types, as I present in the system F, into the category theory. How we can make this translation or this correspondence by identifying the initial and the final coalgebras under this setting. The initial algebra will correspond to the initial object in the F algebras category, and this initial object allow us to define these diagrams that relates the initial object with any other algebra in the category. This arrow is a special arrow called catamorphism, and allow us to define data structures in computer science or in functional programming languages. The dual notion, the final coalgebra, is called or give us a unique arrow, the anamorphism, to map any algebra to the final object, the final coalgebra. And this in the programming language setting is interpreted as co-data types or infinite structures in functional programming languages. So let's see an example. The usual data structure or the basic data structure for any computer scientist is the list data structure. This data structure allows us to store homogeneous data in a unique way, in an ordered way also. And it is described in category theory as the initial algebra under the functor 1 plus a times x. In the initial algebra, the constructor, I will call it in the categorical approach to programming languages, is called the constructor or the injection from the functor or the mapping to the initial algebra. And as we said, this diagram commutes, and the catamorphism is exactly the notion of iteration that we use in programming languages. So for instance, using the Haskell programming languages, we can describe this data type as the two constructors, nil and cons, which corresponds exactly to the mapping or to the morphism that allow us to create a list. And for instance, we have this function that is that calculates or computes the length of any list. And as we can see, we can identify the two cases for the constructors. Under this syntax of the programming language, we can also use a function that is exactly the implementation of the catamorphism for this data type. That is called the folding function or the fold right function. This function allows us to define the same function, but in a more compact way, as it only needs to describe the functions or the mappings that are used to compute either for the base case or the recursive case. And this is exactly corresponding to the last or the bottom arrow in the diagram, corresponding to what we call the step function. This step function is directly defined by the functor and is also depending on the type or the object B that is going to be the result type of the function f or the iteration. But however, if we want to prove or to give a other or to use this idea to give an alternative definition for this function, the function suffices that calculates or that computes a list of the proper suffixes of a given list, we cannot use this same scheme given by the catamorphism. Why? As you can see here, the recursive call or the recursive case of this definition is using the very same element that is given by or is used in the proper call or in the first call of the function. And this is not allowed in the diagram, as we cannot use here a list. We have other structures in category theory, and we can now try to use other mappings or morphisms called paramorphism and apomorphisms to model this behavior that is called recursion or co-recursion. Is the next level of iteration we are using here in the diagram a pair for the paramorphisms, including the a element or an object of the data type defined by the functor f and the initial algebra. And dually, in the other side, for the final coalgebra, we use the coproduct to include or to give an object that is defined by the final coalgebra. In this way, we can define other computational notions as infinite data types or infinite objects in programming languages. And we have here the dual notion of a list, a colist that is a data type that could be empty, but also it can be an infinite list. In the last example, the data type, the list data type, is just for a fixed finite representation of elements under the list constructors, and the colist data type allow us to define infinite elements. Of course, it's just I remark that it's just the definition of infinite elements or objects in a programming languages, as we cannot compute a infinite element or infinite object in any computational model, traditional computational model. So the colist data type is defined as the final coalgebra of the functor c times 1 or plus x, and dually is defined using the destructors or the out mapping that you can see here in the diagram.
Lourdes, there remains 5 minutes.
Yes, I'm resuming. So this behavior or these structures, infinite structures in programming languages can be described using these apomorphisms translated in a programming language. For instance, here I have the code or the definition using the ACDA programming language or the proof programming language. And of course, we need other schemes or other useful notions that allow us to define other types of recursion. And this is the course of value recursion. This notion allows us to define or to use previous results, not just the one previous result of the recursive call, but any result that has been computed before. And this notion uses an extra data structure to keep the record of these results, and is called the isomorphism, as I will show you in the next slide. The more famous example of this type of recursion is given by the Catalan numbers that use not only the previous result or just two previous results like Fibonacci, but it needs all the computed results from the beginning of a given input. So the course of value algebra, or also the isomorphism mapping under the categorical notions, is just a mapping that allows us to define a function from an initial algebra to any other algebra, but recovering or keeping in a record all the history of the of the previous results. And this is given by this definition of F course of value algebra using a special functor that depends on a given object of the category. We also can, not using the duality principle, but also the recursive ideas or the recursive notion, and define the recursive FCV algebra. Here, the important thing, or the most remarkable thing, is that the in and the out morphism or arrows defined by the initial algebras are isomorphic. And due to this fact, we can give a combination of several morphisms, anamorphism, catamorphism, apomorphism, or paramorphism within the isomorphisms. And this gives us very large combinations of diagrams and also definitions or principles that can be used to be implemented in a functional programming. So just closing, this was a very briefly review of the way some computer scientists, including me, we see the types under the categorical perspective. And just to remark that category theory is a new way, or is an extra way to understand computations. Also to review notions and contribute some other ideas to programming languages. For instance, the preferred programming language, Haskell, the functional programming language, but also other programming languages that give us other very expressive systems to define more programs, or also to give the definition of theorem provers as the Coq theorem prover. So thank you. Hope it was a different presentation, and here are some of the references I used.
Thank you very much. Are there any questions?
I have maybe a remark. There might be some convergent points with the books by Bartosz Milewski, who also created a lot of interesting YouTube lectures. He was my colleague. We studied together in Wrocław years ago. And so yes. I thought, so you know him, right?
Yeah. I follow him personally. No, unfortunately I didn't know him, but the last semester I gave lectures about these all foundational ideas for computer scientists, and I used to point my students to his videos and explanations about category theory for computer scientists. Okay, he's a very, very nice reference for many people. Yes, thanks.
I put his name to our chat so you can,
yes,
and everybody else, you can easily Google it up. All
okay.
Right.
Thank you very much.
Thank you.
Any other questions or comments? Okay, if not, then let's go to the other speaker. David Spivak, please.
Yes, can you hear me okay?
Yes, Lourdes, can you stop your sharing?
Yes. Now I have the same problem as Francisco because maybe.
That's okay. So David Spivak, please.
Okay, you can hear me, you said?
We are listening to you. Yes. Now
okay,
we see your desktop. Okay, it's okay.
See the screen? Okay. Great. So thanks for inviting me. I'll be talking about dynamic rewiring as learning. And I am amazed that I'm afraid I've never heard of Dr. Zbigniew Osif. I don't even know how, I've heard other people pronounce his name, Osivich. I am really surprised because I love applied category theory and I love operads, and to receive this email, to know that this has been running for so many years, decades, is really amazing and surprising. And so I saw that Dr. Zbigniew mainly thought about Clifford algebras, it seemed, and things like that, which seems far from what I do. But I guess as a person and just as a community leader, he really brought people together. And I also aspire to do that. So thanks again for the invitation. So I want to talk about a level agnostic description. So what do I mean by level agnostic? I mean, some people call it continuous with respect to sub-agents. So imagine that you're an agent, but inside of you, you have many sub-agents. And maybe you're actually part of some super agent that you don't know about, like the economy or the ecosystem. And inside of you are all these sub-agents, and your brain is also doing some work, and your liver is also doing some work. And so whatever sorts of notions that I'm looking for here should be continuous with respect to sub-agents, or the way I wrote it here is level agnostic. And so I'm looking for a level agnostic description of the sort of thing we see in systems and control and agency. And so here's a little funny picture of some kind of weird being. And this weird being has an interface, and that's drawn here in this circle. And the interface separates what's inside of it from what's outside of it. And outside of it is what its tail can do, which is your arms and your legs and your voice box. And these put you in positions. As I'm speaking right now, I'm moving through position space in a certain way. My voice box is resonating in a certain way, but I can also move myself through space and reconfigure my body, and in general, just put out outputs of various sorts. And in another level, another thing that can happen is that I have a sensorium. Some things come into my eyes, so I have inputs. But what I'm able to see can depend on where I am. So if I close my eyes, then I can't see as much. And as I move into a tunnel, I can't see as much. But what I can see at any point, I mean, how do you describe that? You could describe it as inputs or the sensorium. Sometimes I like to call it directions to remind us of tangent vectors. And so what I'm talking about mathematically here, maybe I should have drawn it like this with the tail on the bottom, your feet and your eyes, and this is controlling your position. And whatever position you're in some base space B. So suppose you have a topological space B, and that's where you can move around in. So this is you, this green dot there. And as you move around, the things that can come in through your eyes are the fiber of this bundle. And so you're moving around through state space, through position space, and then what's coming into your eyes are these directions. So the mathematics here is that of bundles. And so just to say, what are we going for here? This could be seen in places like Boolean circuits, where the positions of the circuit is what it's outputting now. Just like me, my voice box or my position in space is kind of my current output. Anyone who sees it, knows something about me. The inputs do not change for the circuit. They change through time, but the type of the input is always the same. It's always, say, 3 Booleans or 1 billion Booleans or whatever it is, but the circuit has some input and output. For a person, maybe they're outputting their voice and their arm position, their leg position, and then sometimes if they output certain leg positions and move themselves in certain ways, they see different thing in their eyes depending on that. But let's just pretend for this picture that the eyes and ears are what's coming in. Etc. And so for a dynamical system in general, you might output some projections of where you are in state space or phase space or whatever, but incoming maybe are some fixed parameters, or maybe there are some parameters that are moving in time. And so if you imagine a vector field, if you like that sort of thing, you could imagine a little point moving through a vector field, just always moving tangent to that vector field. But then someone's got a joystick, and that joystick is what's coming in. and they are affecting with their joystick, they're affecting the vector field and moving the actual vector field around so that where the arrows are pointing is different. So that's one thing I want to talk about today. And the second thing, I think I started at 35, so I'll probably try to end at 35 or a little bit before for questions. So the other thing I want to talk about is wiring diagrams. And here's a picture of a wiring diagram where we could imagine putting the circuit into one of them and the person into one of them, etc. And of course, the input type and the output type have to match, so that didn't work out quite right. But oh, that one should have gone here. See, 3 inputs and 2 outputs. And so, I want to wire together these interacting dynamical systems. You and your computer and some other dynamical system are put together in some larger dynamical system. And from the outside world, they may not be able to see all this stuff. They can just see that on the outside, you're outputting some things and you're inputting some things. And even more generally than one of these wiring diagrams is something I'll call an interaction pattern. So that's the story I want to talk about, is these sub-agents inside of an agent, each one doing their own thing. But really, so that's something you can talk about with wiring diagrams, and there's an operand for it. And I'll get to that in a little bit, although I won't define it very technically. But what I want to talk about is changing that interaction pattern itself dynamically. So what I want is, like, here's the deal that I'm really interested in, is that on Zoom, we're on Zoom right now. And so what I'm saying, for whoever's listening, my position, what I'm saying is coming into your ears as input. But after we're done here today, we're all going to leave, and then you'll be talking to different people. And so the wiring diagram itself is changing in time. So right now, I'm connected to you, and maybe I'll get feedback from you and stuff like that. But later, I will be connected to someone else entirely. That they're currently connected to themselves or something. And so what I want is wiring diagrams that can change, or even more generally, interaction patterns that can change dynamically based on the states of the people or the systems involved. So when you connect to Wi-Fi, you're changing your interaction pattern. Now there are people who have done this sort of thing before. I'm thinking of Milner and communicating agents and things like that. But I personally feel like that stuff, although done categorically, was a little bit ad hoc. And I'm looking for a language that's general enough that it will resonate with a large number of people, and just kind of work very, just like Clifford algebras or groups or rings or things like that tend to really work throughout a lot of mathematics. I want a type of system for what I'm talking about here that works throughout mathematics, that has that kind of crystalline resonant structure that is not ad hoc to this particular problem, although it works very well for it and actually fits it perfectly. What I want to talk to you about today, which is called polynomial functors, is a very general, well-beloved system that works in lots of parts of mathematics. So I want to say that credential-wise, polynomial functors are not just what I'm going to talk to you about today. They've been studied by the biggest names in category theory. They are studied by Andre Joyal and Ross Street and Richard Garner and all sorts of people. But they are also really well suited to the sort of thing I talked about above in the introduction. So what is it? Well, you fix a convenient category, or what, a topos, if you like that word, but of spaces. It could be the category of sets, if you want to look at discrete dynamical systems, or it could be the category of some sort of convenient category of topological spaces, but I'll call it S. You can think of S as spaces or sets. And a polynomial in S is a kind of strange word, but because it doesn't look like one, when I'll tell you what it is, it's a map E to B. It's a map of sets E to B, or it's a map of spaces E to B. It's a bundle. But the reason we call it a polynomial is, well, there's a bunch of reasons. I'm not going to really be able to get into it, but you can write it as a polynomial in one variable, y. Y is kind of standing for Yoneda there. If that helps you, if it doesn't, don't worry about it. It's just a formal variable. We can write this as the sum over all b in B of y to the fiber E of B. And so, but what's weird about these bundles is if you know algebraic geometry, these are more like maps of schemes. Like B would be a space and E would be a sheaf, if you like that sort of thing. If not, what's weird about these bundles is that the maps go forward on the positions on the base space, and they go kind of backwards on the directions. So to give a map from one bundle to another bundle, I give a map forward called report. It takes, so here's what this is for those little dynamical systems that are running around and giving positions and taking in directions. It's what you're supposed to imagine is that you are entering some avatar, and this avatar is a body that's a different body than yours. You're this body, you're this blue body, and the avatar is this green body. Well, if you're going to enter this avatar, what would you need to feel safe? You would need that your positions, what you're feeling or expressing, is reported to the avatar as something that it's expressing, it's able to express. And then to feel safe, you need to know that for any input the avatar can have in the position you are in, well, let's pull it back. So let's think of it as a position the avatar could be in, an input the avatar could get in the position you are in, that any input it could get could be reported to you as what you should do next as your input. And so from the point of view of algebraic geometry, if you like that, you have a map from, there you have these, if you don't know what that is, what algebraic sheaves are, don't worry about what I'm saying right now. But imagine you have a space X and a sheaf on it and a space Y and a sheaf on it. Then you would give in algebraic geometry a map from X to Y and a map from the pullback of OY to OX. And that's what we're saying here. So that's what a map of polynomials is. And the word polynomial is weird because it sounds like, y squared plus 2y plus 1, but that does count as one of the sorts of things we're talking about in discrete world. We're just talking about this in a more general setting. Now, the setting that we're going to want for dynamical systems is that the avatar is this guy here, is some space, some input outputs world there, some bundle. But the input, what you are, or what's inside of this avatar is Rn and the tangent bundle on Rn. And so you would report where you are in state space to the outside world. Then the outside world would give you some input, and you would take that input and take the pullback here and map that to your tangent space. So basically what's happening is your position is some point in state space, Rn, and a direction you can get in through your eyes is a tangent direction at your point. And here I'm drawing a little Mobius strip to show you that the sorts of directions you can get might change as you move around the circle. I think I'll just ignore that for now. Now, inside of polynomials are what are called monomials. These are ones that are like a y to the b. Instead of a y to the b plus some other thing, y to some other thing, which would be a polynomial, a monomial is just a single one of those. And these monomials correspond in the bundle world to trivial bundles, because basically this fiber is staying the same regardless of the position. And so monomials are a special case that I think are good enough for this talk. They don't represent systems that can open and close their eyes, but if your inputs, if what can come into your eyes, the type of inputs is the same no matter what you do with your body, then that's a pretty good special case. So these correspond to bundles of the form A times B over B, a trivial bundle with fiber A. And I'm going to denote it by to the A, or output y to the input. And again, y is just a formal variable. It's just notation. It corresponds to a representable functor, if you like those terms. But if you just want to think about little systems that are moving around in space and opening and closing their eyes or whatever, and sending data to each other, we don't need that. Okay, so a polynomial map is what I said, and I'll just go on because I think I'm going a little too slow, but not much. Okay, so for a system of ODEs, that is a special case of a map of polynomials. I said what a map of polynomials was up here. It was all this kind of crazy diagram stuff. But you'll see that a system of ODEs, of ordinary differential equations, actually is one of these cases. So if you like those are what dynamical systems are made of. We'll get there now. So inside of this thing is Rn with its tangent bundle. And we would write that as the sum over points in Rn of y to the tangent space at that point. And we would denote it in terms of these pictures where there's all these little doohickeys running around sending each other information. We would denote that as though it was taking in A inputs and giving out B outputs. And we would write this. We would write that this is the little avatar body, and inside the body is this tangent bundle thing. And so what is a polynomial map there? A polynomial map there will consist of two things. It'll take every point in your state space and output some B, so that the outside world can see something about what you're feeling. And then, given a point in state space what you're feeling, and an input A, you will get a tangent vector at your point, which says a direction to move and kind of how fast to move in that direction. And so a dynamical system, that tangent vector should be at the point you're already at, so this should commute. And that's exactly what a polynomial map does. So the word polynomial sounds weird, but it's got the credentials of these great category theorists who have thought about it, and it's got the application to dynamical systems that polynomial maps from the tangent bundle on Rn to an arbitrary by to the A would be a system that runs around through Rn state space, outputting some element of B and inputting a parameter from A that can change in real time. So you're inputting this joystick that's controlling your vector field. And so a system of ODEs is one of these things. It's like an x dot equals f of x, maybe with a parameter. And that parameter is coming from the outside world, that joystick. And then you're reading out. So you have some dynamics, f dyne, and you have some readout, f readout, and you're putting out some B to the outside world that's going to be used by somebody else. And so just for notation, I'll write sys of by to the A as the set of all possible dynamical systems you can put in there in an interface BA. So what can you put in this thing that's outputting B's and inputting A's? Well, it's a choice of natural number, and then it's a polynomial map from this tangent bundle on Rn, on that number, to by to the A, which is exactly what we said a dynamical system was upstairs. So polynomial functors really give you the kind of dynamical systems you want. But polynomial functors also give you wiring diagrams. Oh, the previous speaker, Lourdes, was talking about algebras and coalgebras. And by the way, polynomial coalgebras and algebras are what give you those algebraic data types and codata types. So if we were looking at sets instead of spaces, everything I'm saying would also work. And that's something I'm really interested in. But anyway, so wiring diagrams are also something you can do, because what you can do is you can take these little dynamical systems, one in the sensor, one in the controller, and one in the actuator, and put them together based on some wiring diagram and inside of Q1 here. And Q1 is another dynamical system. Sorry, it's another interface with two inputs and two outputs, say. And so down here, I've drawn a kind of operad style where phi is how this thing is working, this wiring diagram, and psi is how this outer wiring diagram is working. And we're putting them together to get the yellow things. The yellow things are inside the blue thing. The three blue things are inside the green thing. And that's all being drawn here in this kind of operad diagram below. And so wiring diagrams form an operad. Okay, I don't know what that is, sorry. So wiring diagrams form an operad. And what I'm saying here is if you have these interfaces for sensor, controller, and actuator, and you have these interfaces for the physical plant and a human, then you could say, well, the controller will send a signal to the actuator, but also to the human to see, so the human can see what's going on. And the human will send in a signal to the controller so that it knows what it has something to say to the controller. Oh, change your control signal, change the thermostat setting. And then the thermostat is also speaking to the controller, telling it some stuff, and the controller is telling the furnace to turn on and turn off. And that goes to the physical plant that actually does turn on and turn off, and we get some temperature as a result or whatever. And all these things are polynomials, and inside these boxes are polynomials, and inside the polynomial boxes are dynamical systems. And when I write tensor here, the tensor of two polynomials, if P is some positions y to the P bracket I, and Q is some positions times y to the Q brackets j, then the product here is just you take a pair of an I and a j. So position of each in P times Q, P of 1 times Q of 1 of y to the P bracket I times Q bracket j. So you just multiply positions, you multiply directions, and that's what tensor means. Or if you like bundles, I guess I'll use E1 and E2 instead of P and Q. So here's kind of the P bundle and the Q bundle, and we want to tensor them. It's just the thing you would hope it would be. It's just E1 times E2 mapping to B1 times B2. And so when I'm writing these lots of boxes inside of a single box, I'm tensoring them together. I'm tensoring their behaviors. Okay, so not only ordinary differential equations, but also wiring diagrams are maps in Poly. So Poly, for whatever topos S you are in, sets or spaces or whatever you like, Poly not only tells us, maps in Poly not only tell us what a dynamical system is, but also what a wiring diagram is. So we can just compose easily and everything works very, very nicely. And so maps from P1 through PK, all tensored together to Q, is putting a bunch of little things together inside of a Q. We have all these little P's inside of a Q interface. And let's say I'm putting K many things together. So here K is 4. 4 things inside of a thing. There's a kind of interaction pattern of one of these polynomial maps gives you an interaction pattern or a soup or something where you've got these little P's inside of a bigger Q. And what they're doing, they're updating their own state. And Q is hearing the outside world's point of view on things and sending it to the P's. And the P's are changing their internal states based on what they're hearing from each other and from Q. And they're sending data to Q. And all of that is what polynomials can do. Well, it turns out that Poly with tensor is what's called monoidal closed. And that means that there's an internal hom, P bracket PQ. Now, you don't know what internal hom is necessarily. Maybe many of you do. But what can we say? First of all, this generalizes polynomials themselves. So polynomial maps from Y is the dynamical system, is the interface 1 to 1. So maps from this to P, E to B, it's not a set of them, it's a polynomial of them. PQ is in Poly. And so this generalizes P. So, okay, YP is B. All right. But what is it for, something like this? What if I had a little AB dynamical system? I guess I actually wrote it this way. A BA dynamical system and a B prime A prime dynamical system. Then this shape here is a new polynomial that outputs interaction patterns and takes as input what's coming into the space from the inside guy and what's coming into the space from the outside guy. So it takes the outputs of the inside guy and the inputs of the outside system as inputs. So that might sound pretty complicated, but that's just what the math says. Luckily, what the math says is useful. So what you should think of is a CEO of a company. And the CEO of the company is everything okay?
5 minutes.
5 minutes, great. The CEO of the company has a job. They arrange the inside players, P1, P2, and P3, to do some work and send each other information. And then they also figure out a way that inside information gets published to the outside world. So the CEO is taking what's going on inside and giving an interaction pattern. Here's how you take what you did and move it to the outside world. And so what it's outputting, what the CEO outputs as their job is the interaction pattern between the internal guys and the outside world. And what the CEO inputs in order to change its behavior and to update its state, what the CEO inputs is the outputs of those internal players and the feedback it gets from the outside world. And that's what the CEO inputs. And the CEO changes the wiring diagram based on what it sees. So we can look at systems, dynamical systems that play the role of CEO. And the dynamical system is changing through time, its internal state, based on what's being output by the internal systems and what's coming in from the outside world. And then it outputs a new interaction pattern, the whole pattern itself. That's what the CEO outputs. Now, if we do systems on just with no internal boxes, so if I'm just P and I have no internal boxes here, then I recover systems on P, which we talked about before, dynamical systems in general. So when K is 0, you get parameterized dynamical systems here. But when K is greater than 0, we get these interaction patterns. We're outputting interaction patterns and we're inputting what's going on and we're changing our state from that. And so we get an operad, or a categorically enriched operad, by nesting these. So the objects are the polynomial functors, which are just these E to B things, and outputs and inputs, and the morphisms are dynamical systems on wiring them together. So these CEOs are the morphisms. Now, the punchline is that the same structure, the exact same structure, comes up in deep neural networks. Now, deep neural networks were big, 5 years ago, and people still think they're pretty cool. But what do they really do? Well, I mean, they're an amazing thing for classifying stuff. And in a paper called Backprop as Functor, we looked at the structure of neural networks. And it turns out that these neural networks, the way that we do gradient descent and backpropagation, is just one example. And it's exactly the same structure as I've talked about here. That the red things, these neurons, if we turn them sideways and look into them like a telescope, so where you see lots of things coming out, that is the operad. We turn them inside out and sideways, and we see these wiring diagram things here. And so it appears that we can take, like from the math, it seems that we can put ODEs exactly where we put neurons in deep neural networks and get real-time learning from continuous time signals in exactly the place that the deep neural networks do discrete time learning from training data. They are living mathematically in exactly the same part of the theory. One is for the category of sets, and one is for the topos of spaces, but they're exactly the same structure. So I'm interested in people's thoughts, but that's my talk. Thank you for listening.
Okay, thank you very much. Are there any questions or comments? No? Okay, so we thank again the speaker, and we go to the following talk. Next talk, Francisco Martinez.
Yeah, I'm here. Can you listen to me?
Yes.
Correctly? Super. Let me share my screen. Okay. Now you should be able to see it, my presentation, right? Oh, let me go to the beginning. Well, just a quick comment on the last presentation. It was pretty cool, the diagrams and all. So hello, everyone. Thank you all for still being here. Let me first start apologizing because I am robbing you of some of your lunchtime, but you can eat while I give my presentation if you want. I promise I won't judge you. I cannot even see you, so I won't judge you. But that's not on me, that's on the organizers, because this is the only talk scheduled at this time. But anyways, thanks to the organizers for this amazing event. And in particular to Carlos Cesar Jimenez, because he's the one who encouraged me to present some of my work here. And also I'd like to thank Luis Estrada Gonzalez, because I discussed some versions of what I'm about to present to you with him. Actually, I wrote the paper on which my presentation is based under his supervision. So thanks to Luis Estrada Gonzalez. So I'm going to talk to you about kind of odd topic, which is paraconsistent theories of computation. I will tell you how I think we can model these kinds of theories in toposes. But first, let me give you some preliminary points before I start. So I will be assuming throughout the talk a pluralistic stance. This means that I believe that besides classical mathematical theories, that is mathematical theories based on classical logic, we also have interesting and legitimate theories that are non-classical. For example, intuitionistic theories in which the law of excluded middle is invalid. For example, Halting arithmetic, synthetic differential geometry, etc. But we also have some stranger theories, which are paraconsistent theories, in which the rule of explosion or ex contradictione quod lidet is invalid. That means that in this kind of theories, we can have contradictions without triviality, right? From a contradiction in these theories, not everything will follow. So some examples of these kinds of theories are relevant arithmetic, naive set theory, and actually paraconsistent computability theory. There are other theories like contraclassical theories, but I will be focusing mostly on intuitionistic theories and paraconsistent theories in general. Another thing I'd like to highlight is that my discussion of computability comes from foundations, not so much from practice. That means that my references are not computer scientists doing computability theory or physicists. It's people working in logic, particularly people working in non-classical foundations for mathematics. So yeah, it might be not for the best taste of everyone here, but that's where I come from. And what I will be, the general question that frames my presentation is how to compare theories of computation based on different logics. What I will propose is that we can compare different theories of computations using topos theory. I think topos theory gives us enough tools to do this, right? So here's the plan of the talk. Probably some of you are already worried that I am talking about paraconsistent logic in toposes, because I think it was Professor Kaufman, the one who mentioned just a few hours ago that in general, the logic of a topos is intuitionistic, and that is very far from being paraconsistent. So the first part of the talk will be devoted to explaining how can we interpret paraconsistent theories in general in toposes. This part of the talk is not mine at all. I borrowed from Chris Mortensen, William Laverse, and Luis Estrada Gonzalez's work. And yeah, that's the first part. I will present to you a method to dualize the internal logic of a topos in order to obtain dual intuitionistic logics inside toposes. The second part of the talk, I will apply this method to the case of the effective topos, which is, I think, a very good case study, because some people have thought of this topos as a universe of computable mathematics. So part of the, what I will do in that part of the talk is to tell you why people might believe that the effective topos is a universe of computable mathematics. I will talk to you a little bit about its logic, but what I will be mostly interested is in applying the method mentioned in the first part of my talk to this topos in order to obtain a model of paraconsistent computability theory. This thing that I will call complement F has very odd features. It is an inconsistent topos. The theory of this topos is inconsistent, but it's not trivial. And I know that's very odd, but I will give more details in due course. And I will close with some remarks on foundational issues. So let's go ahead. First, this is very standard. You all know that what characterizes a topos and differentiates it from other sorts of categories is that it has this thing called an object of propositions or an object of truth values and a subobject classifier. So we usually refer to this object as omega, and we say that its global elements are propositions and its generalized elements are propositional functions. In particular, we have some propositions that can be thought as truth values. The standard story will tell us that one of them is the value true and the other one is false. And I will say more about it in a minute. But apart from that, we know that the propositions, the global elements of this object form a partial order, and that we can define logical connectives as certain operations of omega, right? That is, certain morphisms to and from omega. And we say that the logic of a topos is the algebra of operations of omega. All of that is standard. All of that, you should already know all of that. So the standard story tells us that the logic of a topos is in general intuitionistic, right? That is because the algebra of operations of omega is described as a Halting algebra. So, for example, as I mentioned before, we have this proposition that I write here as nu, which is the subobject classifier. I will not read all this. This is basically the comprehension axiom, but it says that if you have a propositional function phi and an object O of the topos, then phi of x equals that truth value, the one we are considering, if and only if x is in M, right? Here M is a subobject of O, of the object O. So the standard story, the standard reading of nu is that nu is the value true, right? So then the previous axiom, which is the comprehension axiom, states that phi of x is true if and only if x is in M. M, remember, is the subobject of O, which we are evaluating. So a natural understanding of M would be that it is the extension of the propositional function phi, right? That is the part of O that satisfies phi. And if we think of nu as the value true, then this alone induces a particular ordering on the propositions, that is on the global elements of omega, and a particular labeling of the whole logical vocabulary of the topos. So for example, we can consider a connective, which I will signal here with this sort of times symbol, that has a domain in omega, the product of omega with omega itself and as codomain omega, as the characteristic of the pair nu and nu. And so if we choose the name true for the morphism nu, then a natural reading of this connective is as a kind of conjunction, right? Because it basically tells us that whenever you have a proposition P and a proposition Q, it will be equal to the truth value true whenever P is true and Q is true. And that is, of course, the truth condition for the conjunction. So if we start labeling nu as true, we should better call this connective as a conjunction. And we just do exactly the same for the rest of the logical vocabulary. We define another proposition false, we define negation, we define disjunction, and what we get, of course, is a Heighting algebra. The algebra of operations of omega will be a Heighting algebra if we start with this reading of nu as true, right? So that's why the standard story tells us that the internal logic of a topos is in general intuitionistic. But there is another way to proceed, actually. As Mortensen and Lovers and Estrada Gonzalez have pointed out, this standard story that I just told you about nu depends, about the logic of a topos, depends on a particular labeling of the truth values and of the logical connectives. So they ask us to consider the following. What if we think of nu as the value false? So then the comprehension axiom would state that phi of x equals false if and only if x is in M. So in that case, a natural understanding of M, remember M is the subobject of O. So in that case, a natural understanding of M would be not as the extension of the propositional function phi, but as its anti-extension. That is the part of O that doesn't satisfy phi, right? Because phi of x will be false if and only if x is in M. And this is only changing the labeling of the morphism nu, the subobject classifier. And this decision has an impact on the whole labeling of the logical vocabulary. So going back to the connective, to the conjunction in the standard labeling, now with this reading of nu, we should better call this connective a disjunction, because it will give us the falsity condition for disjunction. It will tell us that P connected to Q via this connective is false, equals false, if and only if both P and Q are false, right? And that is the standard falsity condition for disjunction. And it happens the same with the rest of the logical vocabulary, at least with the standard logical vocabulary. Instead of conjunction, we will get a disjunction. Instead of a disjunction, we will get conjunction. Instead of implication, we will get something called subtraction, and so on. So just to summarize this method, we take a standard topos with a standard labeling, and we relabel beginning by the subobject classifier. Instead of calling it true, we call it false, and then we define the rest of the logical vocabulary accordingly. And what we get is what people call a complement topos. And this complement topos, its logic, it's not intuitionistic. It induces the order of propositions induced by this labeling and the algebra of operations of omega induced by this labeling. It's not a Heighting algebra, but a Brouwer algebra, which is dual to the Heighting algebra. And the logic induced by this is not intuitionistic, but dual intuitionistic. Actually, it is called closed set logic, and it is a kind of paraconsistent logic. So actually, it validates the law of excluded middle, but invalidates explosion. So it allows us to have paraconsistent theories in toposes without triviality. And that's basically the method. You take a standard topos and you relabel the logical vocabulary beginning by the subobject classifier, that is by nu. Now let's apply that to the case of the effective topos. So first of all, let me say a bit about this topos. why people think that this is a universe of computable mathematics. At least I have heard it say from Andres Bauer, a person working in this topic that has worked a lot on this topic. So the objects of these tuples are equivalence relations between assemblies. I will tell you in a moment what are assemblies, and its morphisms are functional relations between those equivalence relations. So just very briefly, the building blocks of the effective tuples are assemblies, and it's actually pretty much easier to work with assemblies than to work with the effective tuples. So let's see what assemblies are and why people think that this tuples is a universe of computable mathematics. So an assembly is simply an structure set. It consists of a set and a relation such that for every element of the set, there is a natural number that is related to that element. So the idea behind all this is that for every object in our category, we want to have a computational representation of it. So it doesn't matter if the set A is non-denumerable. Actually, we can assign the same number to different elements of the set A. So the idea is simply to have a computational representation of each and every one of its elements. And that's why we read this relation between n and a as n represents or realizes a. So given two assemblies, we say that a realized function between such assemblies consists of a function f prime from the underlying sets, such that for every element of A and for every natural number, there is a partial recursive function that satisfies this formula. So it basically says that if n realizes x, then the partial recursive function p, when applied input n, is defined, and the output of that computation is the representative in B of f prime of x. So in words, is just that the partial recursive function p acts on the codes or representatives of the elements of A in a similar way as f prime acts on the actual elements. And of course, assemblies and realized functions form a category, and it is a full subcategory of the effective tuples. And now, a very nice feature of this is that the category of assemblies has a natural number subject. And there is a particular theorem that holds for this category, which is that every numerical morphism is total computable in it. So this means simply that for any assembly X and morphisms with X with domain X and codomain, the natural number subject of the category, we have an effective method to compute X followed by F, right? And what is even better is that the inclusion functor from the category of assemblies to the effective tuples preserves the natural number subject. So this thesis, which is called the extended Church thesis, is also true in the effective tuples. That is, every numerical morphism in the effective tuples is computable. So we can frame that in internal logic of the tuples, as I put it here. Here in this extended Church thesis, D is Kleen's D predicate and U is Kleen's output function. So T, E, and Y just says that Y is the code for a complete calculation of the F partial recursive function when applied input N, and U of Y gives its output, right? So assuming an enumeration of the partial recursive functions, the extended Church thesis says that every morphism F from N to N is the F partial recursive function for some number E, right? So now we can see why the logic of these tuples is intuitionistic and it is not It is not classical because it's basically a restatement of the halting problem, but with other resources. So you consider a morphism from the natural numbers of the topos to the natural numbers of the topos, and that says that the n partial recursive function, when given input n, returns output m. In that case, E of n equals n plus 1. Otherwise, E of n outputs 0. It's equal to 0. So assuming for reduction that the law of excluded middle holds in F, it would be the case that we have this large disjunction. It would only mean that this function, this Gothic E, would be totally defined for all n of F. And since the extended Church thesis is true in the effective topos, this function would have a code E. But that would imply that E applied to E equals E applied to E plus 1. But this obviously contradicts some basic arithmetic facts that also hold in F. For example, that for every number, it is false that that number equals its successor. So, closing the reductio, we have that the law of excluded middle cannot hold in F. So those are the features I wanted to mention about F. But now we can apply the method I mentioned very briefly in the first part of my talk to this case, and we can dualize its logic. So instead of having an intuitionistic logic, something I didn't mention is that to apply this method, we need that the topos is not Boolean, because dualizing a Boolean algebra gives us back a Boolean algebra. So then we wouldn't have a different logic of the topos. For example, the complement of set is set itself. But in this case, since the effective topos is strictly its logic is strictly intuitionistic, then we can apply the method, right? So, but let's remember that the relabeling method doesn't add or subtracts a structure. I will hurry up. So both the effective topos and complement F are isomorphic. So for any object O and property P, this object O has the universal property P in the effective topos, if and only if O has the universal property P in complement F. So in particular, we have that the complement F preserves the natural numbers object, it preserves products, it preserves coproducts, it actually preserves every other categorical structure. So this means in particular that the extended Church thesis should be true in complement F. And we can rephrase it in the language of complement F.
Francisco, 5 minutes, please.
Yeah, I will hurry a lot. So we will just take like the analog of the morphism that we were trying to use before. I will not read all this, but now in this case, we know that since excluded middle is valid in complement F, we have this large disjunction, but that gives us the result that there is a number m such that it is equal to n plus 1. This is a result that we can obtain in this topos, in this complement topos. And that's obviously just, very, very odd, but it gets it gets stranger. So assuming that the standard F is not trivial, then we know that in a standard F, there is a number such that that number is different from its successor. Actually, this is valid for every number. But dualizing this statement, we have that for every number in complement F, that number, it's also different from its successor. So in particular, we will have that it is not the case that m equals n plus 1. So we have an explicit contradiction, right? On the one hand, we have that m equals n plus 1, And on the other hand, we have that it is not the case that m equals n plus 1. And that's really odd. That's really, really odd. So given the failure of explosion, that doesn't mean that this contradiction will entail any arithmetical formula whatsoever. And actually, we can say something a bit stronger, and that complement F models a non-trivial theory of computation, because it would be trivial only if a standard F were a trivial topos. Because remember that F and complement F are isomorphic. So one of them would be trivial if and only if the other is also trivial. Now there is also, we can talk about the halting problem there, that it also causes a lot of trouble in complement F. But yeah, what I will close with this. I haven't tell you at all what to make of these kind of cases, how to make sense of inconsistent computations. But that's a story that people have already been saying some things about. In particular, Zach Weber has written about it. Graham Priest has written some stuff about it. Richard Routley, Jack Copeland have mentioned some things. So you can find some people that make sense of this whole thing. But yeah, there is also the question on, I showed you in this talk how we can obtain a paraconsistent computability theory out of an intuitionistic one, but it applies only to toposes, right? Because we are considering the logic of a topos in particular. So there is the question of how to generalize this approach to other categories. And a very different question is whether or not we need the natural number subject to formulate theories of computation. If we want to talk about, if you want to ask me about foundational issues, you can ask me in the questions. Otherwise, we can go to it. But yeah, I will finish right here. Thank you.
Okay, thank you very much. We have a comment on the chat from Professor Michael Heather. A topos has no value false, and it seems misleading to call it a topos. It leads to paradox, which as Whitehead points out, indicates error in antecedent reasoning. How do you think about that?
So no, in the standard toposes, you can of course define a morphism called false. Actually, in most toposes, in every non-trivial standard topos, you have the morphism false. So you do have that. I don't know why you wouldn't have that. I mean, what is strange here is to rename true as false and get all the other stuff. But you do have, in the standard story, you have false already.
Okay, thank you.
Yeah, if they want to elaborate, that's okay.
Are there any questions, any more questions or comments? No, I don't see any more.
I see Carlos Cesar Jimenez with his hands up.
Yeah, please.
Thank you. Thank you, Francisco. Very interesting talk. Well, I just have one question, and it's related to what Walter Carnielli is doing in Brazil. I want to know if you think that what you are showing us today somehow is connected to what people in Brazil is calling a consistent Turing machines. Is it connected somehow? Could it be connected somehow? That's one part of my question. And the second part of my question has to do with quantum computing. Because, for example, people in Brazil, like Carnielli and so on, are saying that these paraconsistent Turing machines somehow are similar to these quantum computer models. So do you think that the topos model might be a better fit to modeling quantum computing. And well, that's it. So those two parts, a relation to paraconsistent quantum machines and to quantum computing.
Yeah. About quantum computing, I have nothing to say about it because I really don't know about the topic, so I really cannot answer that. So I simply don't know. But about the first, I think it's sort of a different approach, because if I understand correctly, Agudelo and Carnegie, or Carnelian, at least Carnegie, I think, they are trying to conceptualize paraconsistent machines in terms of more familiar operations. So for example, I think if I just read one paper from them, and they think that what we call, or what broadly called paraconsistent machines, they can describe them as non-deterministic algorithms or something like that. I honestly, I haven't told a story about what I believe are these inconsistent computations. But I think I am open to different kinds of answers. For example, I also like the answer from Zach Weber that we don't need to reframe these unorthodox features of computations in terms of familiar things, in terms of familiar concepts like non-deterministic algorithms, but we could simply understand them in terms of this unorthodox stuff like naive sets, right? That they are actually weird. They are not the things we're familiar with. So in principle, I'm neutral about the story we are going to say about inconsistent computation, but I'm open to both kind of answers.
Okay.
Thank you.
So
thanks to you.
Thank you very much. I don't see any more questions, so let's finish this session, and we will meet at 4 o'clock in Mexican time in order to have the last session related to geometric algebra. The organizers, do they have any comment?
No comments. Only that 4 o'clock Mexican city times we come back.
Okay. Thank you very much. Goodbye.
Mm-hmm.